Welcome, everybody. I'm Rachel Abercrombie. I think I'm the only earthquake scientist here at Boston University. It's my pleasure to welcome you all here this morning. So we've got some slides that were put together for me here. Yeah, so basically the aim of this little informal workshop this morning, all day, is coming out of a group of folk here at BU in the computer science department, really, and data science, who got interested in trying to use their skills they have developed in AI and other expertise to study earthquakes and earthquake science. And so they reached out to me, and really we're probably in the sort of first year of learning to speak one another's language is probably where we're at here. I'm very happy to welcome all of you here to join in and to get to know one another in the community and hopefully help us all contribute to learning more about either earthquakes or more about AI and hopefully more about how to put the two together to actually learn something useful. So the people organising this or involved in this BU part of the collaboration are Brian Kulis, who's done most of the organisation, who's over here, and Janusz Konrad, who's just walked in, who's an image expert, and they will actually be presenting this afternoon about some of their sort of preliminary work in applying the techniques they've developed in other fields to earthquakes. I'm here as the earthquake representative, and Prakash is joining us shortly, I hope, who's also in the computer science AI team here at BU. So looking at this group of people makes us realize that we've got very distinct expertise here. So one thing I was sort of looking at across here is how many people here would call themselves an earthquake scientist? Okay, right, these are the people you need to reach out to if you didn't put your hand up because you've got burning questions about earthquakes you felt as a child or anything like that. But also, if there are things we say that you don't understand, you're not the only one, but everyone who didn't put their hand up is also not an earthquake scientist, which means that they haven't had intro to seismology and intro to plate tectonics lectures, so they also will have some of the same basic questions you do. So, because that will help other people out. And then who here would call themselves an AI or machine learning or computer science sort of expert? Yeah, okay, right. These are the people the rest of us need to ask when we don't understand what's happening. So, and there's also, I know, some people here from the realms of public health. So, yes, we've got a mixture of expertise, so just, learn from one another. The speakers today, we have 4 speakers. 2, we hope to have everybody in person, but 2, unfortunately, are only, well, unfortunately, we're very glad to be able to have them at all online due to logistical and other changing circumstances. So this morning, we're going to have Tim Clements and Theresa Sawi, who are both with the USGS in California. And then this afternoon, we're going to have Sophie Giffard-Roisin, who is sitting here, and Mostafa, who we hope will arrive in time this afternoon. Mostafa is newly arrived at Harvard University, so hopefully someone we can welcome to the earthquake science community. Come on in, here in the Boston area. Okay, so here's the program. I stop waffling in a couple of minutes' time and introduce Tim, who's with us online. And then we'll have a half an hour with him and hopefully some questions, and followed by Theresa. And then Brian and Janusz will tell us a little bit about work that they've started doing here. And then we hope to have time for some discussion before lunch. We'll have more discussion, and in the afternoon, Sophie and Mostafa will talk. And then we left an hour or so at the end. I don't think they're going to kick us out at 3 o'clock if we are still talking. And really, we didn't know. This can be whatever form we want. If we want to split up into smaller groups to discuss specific topics, that works. If we want to have any kind of breakout, or we just want to have a general discussion, then we're open to all options on that. So I think that's pretty much all I have to say. I think there might be a couple more slides here. One thing I forgot to mention, I definitely put it on one of the slides, which is thank you very much to Catherine and Maria, who are back there, who have been organising it all for us. So thank you very much. And if you have any logistics questions or AV questions, or like I'm about to have, how on earth do I move on to the next speaker? These are the people to ask. So any basic questions before we go any further? Have I forgotten anything obvious? Okay. I think there's coffee at the back. You can't survive without it. Okay, so then, yes, thank you. Connect with us, and I think, yes, can you get us Tim?
Yes.
For me, please. So Tim Clements is a research geophysicist with the USGS, who's actually joining us from New York, where he go at short notice at the moment. I first met Tim when he was a graduate student at Harvard. So I've had the pleasure of knowing him and his work for quite a long time, and I'm thrilled that he can come and talk to us about some of his work on earthquake early warning and ground motions, and the use of artificial intelligence in that.
Hi, Tim. At this time, you can share your screen. Thank you.
Okay. Let's see. Can you see this? Can you hear me?
Yes, we can. And if anyone has questions, we're going to wait till after the presentation.
Okay.
Thank
you. So thanks, y'all. Thanks for having me, especially Brian, Rachel, and Catherine. So again, I'm Tim. I'm familiar with Boston. I was there for a while. And so I'm at the USGS, where the federal government's science organization responsible for monitoring and doing research on earthquakes. So I thought I'd talk to you guys about kind of what our group has been doing lately and using AI to forecast earthquake ground motion. And so let's see. Where I wanted to start was, I think when a lot of people who are outside of earthquakes, they think of, the first thing to think of is, okay, let's do earthquake prediction. And so the idea behind that is predicting the timing, the spatial location, the depth, and the magnitude. The magnitude is the size of the earthquake. And it turns out that this is challenging. I might even say impossible with the current data we have. So we don't do this, and I think for a number of reasons, in terms of, we don't want to be wrong most of the time. So what we do in practice is earthquake forecasting. So this is a little bit different. So it's the idea of thinking about the probabilities of an earthquake occurring over a certain amount of time. And so it turns out after a large earthquake, this is actually a tractable problem. You can forecast the number of earthquakes. And so the USGS, we do this in near real time after large earthquakes. And so I'm showing here is, and I can have my pointer. So there's an earthquake in West Texas last week. And so we put out this aftershock forecast, and we're saying that there's about a 60% chance of a magnitude 3 earthquake happening in the next week in that area. So this is something we do in real time. And what I'm going to argue in this talk is that for AI, I think we should move into not forecasting just the earthquakes, but the ground motion that occurs with each earthquake. So not the event, but with the thing that happens after, which actually is what causes all the shaking, and then which ends up damaging buildings. So it's a slight change in kind of what we do now, but I think it's going to allow us to apply a lot more computation and data to the problem. And so I want to kind of compare and contrast what I think the opportunities for AI in this are. There's just two different topics. The amount of data available and the physics you can take from either think of an earthquake as a single point kind of location and magnitude, or kind of a suite of waves traveling through the earth. And so if you have an earthquake catalog, again, just like the listing of how big an earthquake was and where it occurred and what time, a big earthquake catalog would be maybe 1 million events. And so that's maybe 100 megabytes if you save it into a CSV file. So I tend to think in bits, so that's maybe 2 to 30 bits. Whereas if you took a training data set of all the seismic waveforms ever collected on Earth, maybe that's a petabyte, few petabytes. That's maybe 7 orders of magnitude of more data in log 10 space. And so the other idea is that, thinking of an earthquake as just a point in a CSV file with, 5 parameters is kind of like looking at like a Picasso line drawing. So you get an idea of kind of the figure, this is a sparrow, versus full seismic waveforms. There's a lot of physics going on. There's all these different conditions from the sites. And so you might not be able to distinguish the tail of the sparrow from a leaf, but if you can extract all the information possibly, there's a lot more available there. So I think moving towards AI on all of the data, I think we're in the all data kind of regime is where we should be moving. And so I think there's been kind of 2 different kind of frameworks that have emerged in the last 10 years in AI that I think are really specifically helpful for earthquakes. And so the first is doing deep learning on graphs. And so about 10 years ago, we had the convolutional neural network revolution. And then a few years after that, folks started applying convolution to non-Euclidean domains. And so this is, what I'm showing here is if you do convolution over a graph, it's basically doing a graph neural network. So this is really powerful if you have non-Euclidean data like we get in earthquake science. And so over the, I'd say, last 5 years, people have been using graphs to represent seismic networks. So I'm showing here, this is a set of seismic stations in Japan that I've turned into a graph. So you can connect nearby seismic stations. So each of these nodes would be a seismic sensor. And then if you have the waveforms or the seismic data, so the classic squiggles. So I'm showing here, we record seismic events in 3 components of motion, so east, north, and vertical. So if you put that as the features of your nodes in this network, you can basically capture an earthquake as it travels across the seismic network. This is a very powerful way to represent the kind of random kind of location of earthquake stations, so you can capture a full earthquake. And the other thing that's happened in the last 5 years is the kind of the large scale takeover of natural language modeling of most of AI. And so the really simple idea, I think most people in the AI space know this, is to train these large language models, basically just take some context, so a sentence or a paragraph, and say, in this instance, our company is training. And the idea is just to predict the next thing. And so in language modeling, it's the next token or the next word. And so the idea is to learn kind of the probability distribution over the next word. And so in this case, maybe 50% of the time it would be workers, or 30% of the time it'd be staff, and then maybe just less interns, so 10%. And so if you do this a few trillion times, you can learn a probability distribution over language. And so what I'm going to argue is that maybe we should just do this for seismic waveforms. And from that, we can learn probability distributions over earthquakes and all the physics involved without having to specify it. And so what's been that kind of transformative, are these generative pre-trained transformers. And so take the entire internet and just teach these large models to predict the next token. And so the transformer and attention block is really the thing that's driving this. And so I'm not going to go into the details here, but I think this has really been amazing to see what's happening. And so I think all of our AI and machine learning colleagues, we want to learn from you. How can we apply these to the earthquake problem? So I'm gonna share 2 short topics here. So one is doing this earthquake early warning with this graph-based approach. And then I'm going to talk about applying this generative AI to predicting kind of time series of ground motion. So I'll start with this earthquake early warning with graph learning. So this is a paper we published last year with some colleagues at the USGS. And so we're trying to do this earthquake early warning, which I think was summarized nicely in this publication that came out in 2008 when Japan started doing this. And so the idea behind earthquake early warning is that you have only a few seconds after an earthquake starts to then predict ground motion. And we can do this because basically seismic energy travels at 3 kilometers a second, and electronic communications travel 3 times 10 to the 8th meters per second. So if we can outspeed our predictions of shaking, we can have a public safety program to then tell people where it's going to go. So what this looks like graphically is I'm showing here, this is a map of the Sundai province of Japan. And so if you have an earthquake off in the ocean, it takes some amount of time for the waves that are going to carry the ground motion to travel to the coast. And so if you have a set of seismometers sensing data right on the coast, if you can send that information that there's shaking coming to the people who live inland, you can get up to maybe 5 or 10 seconds of warning, which you can then turn off trains. You can warn the hospital, stop the surgery. You can have people either, what we tell people to do is drop cover and hold on, or you can shut down bridges, things like that. And so here in this map, the darker areas have stronger shaking. So it's not always the case the closest place has the strongest shaking. So we have a system in the US, it's called Shake Alert. It's currently running on the West Coast, but someday hopefully it'll be covering the entire country. And so the classical way to do earthquake early warning is what we call source-based. So we have these seismic networks on the West Coast that are continuously taking in streaming waveform data. And so then we have to locate the earthquake, figure out how big it is, figure out the magnitude. And from those two pieces of information, we can predict shaking. And so what we're trying to do is predict basically a real-time shaking map with data that's coming in. So this is quite challenging. And to be honest, we don't always get it right. And so what we've done the last 5 to 10 years is go from thinking of earthquake as an earthquake happening on a fault to just tracking the wave propagation and using the shaking to predict future shaking. And so this is quite simpler. It's a little bit slower than because you have to keep predicting in real time based on data you receive. And so what I'm going to show you today is what we're just doing is deep learning to learn the physics, but just take streams and streams and loads of previous data to predict future shaking in real time. So we have this model, we're calling it GRAPES. So it's graph prediction of earthquake shaking. And we chose the name GRAPES because grapes kind of look like a graph neural network, which is what we're using. And the idea here is that we take a seismic networks, in this case, we're using Japanese seismometers. We take in data in real time. This is just the raw kind of squiggles that you see. And then at each station, we use a set of neural networks to extract kind of time frequency features, to extract as much information as we can from the waveforms and encode that in a feature vector. And then we do, basically it's graph convolution, but I like to call it seismic telephone. And the idea is that if a certain node in the network senses something that's in previously associated with strong shaking, it can send that information along the network. And then if you do that a number of times, you can then take that information that you've aggregated regionally and then predict ground motion in the future. And so we do this, we train these networks end to end just to predict shaking, but it learns kind of the most important things to extract from the raw data to then predict that final, we call this PGA, peak ground acceleration, which is what actually damages buildings. So to quickly just describe the data we use. So Japan has an extensive network of seismometers covering the entire country, and they have very high seismicity rates. And so we took as many earthquakes as we could from Japan. So I'm showing here on the right, the green is our training data, purple is our validation set, and then the orange is our testing set. And so basically just took each earthquake and then tried to predict through time, kind of what's the peak acceleration throughout the event. Quite a simple setup using the Atom optimizer. And so I'll show you an example that we have from our test set. So this is on the left here is what we call a shake map. So again, the darkest reds are very high intensity shaking. So this would be about 1 G of acceleration would throw you up in the air, basically. And then as you get further away, you basically wouldn't feel the earthquake. And so the idea here is to predict the strongest areas of shaking as soon as possible. And so what I'm showing here on the right is this is the waveform that's recorded by the first station to detect the earthquake. And so this is 500 centimeters per second, about half of a G of acceleration. That's quite a strong shaking. And so I'm showing over on top of this is the activations of the kind of station level local feature extraction network. And so what's cool we found is that these feature extractors basically learned how to pick out different types of seismic waves. So before the earthquake arrives, a set of features are only activated that are associated with basically ambient noise. And then as the P and the S waves, these are the first and second waves that arrive at a station, a different set of features activate. And so basically the network has learned how to extract which kind of waves are occurring. So then that is sent in to basically predict the future intensity. So intensity is the amount of shaking. And so we do this in the log space. So 7 is very high and 0 is basically not felt. And so at this particular location, we can predict the intensity of future shaking. And it turns out that if you're very close to an earthquake, there's almost nothing we can do to predict within a few seconds. And so you'd only get this gray line is what is recorded in real time. And so you get maybe 1 or 2 seconds of prediction. So we wouldn't be able to help you in this case. But if you're further away, what I'm showing here is a station that's about 60, I think 65 kilometers away. The P wave, is the first wave, doesn't arrive for 12 seconds. What I'm showing here are the activations of all the neurons at this station in the graph network. And so what's cool is that when the first wave arrives at the first sensor, the activations all flip. So basically the entire network just learns that there's an earthquake happening. And then you can start, based on that flip in activations at this station, you can start predicting the future intensity at this location much faster. And so this purple is what's predicted at the station, and then the gray is what is actually happening. And so you get about 10 seconds of warning based on learning how waves will travel through the network from its training data. So we took that network and we trained it on data only in Japan, and then we took it and applied it to the Ridgecrest earthquake, which is one of the biggest earthquakes in California in the last 5 years. And so we took our model GRAPES and compared it to the Shake Alert algorithm, which is the USGS's earthquake early warning algorithm that's running on the West Coast now. And so what I'm showing here are, in this top panel, are the observations in real time for this earthquake. So this is, each dot is a seismic station, and I've colored this by the intensity scale that we use in the US. So blue, again, is something you wouldn't feel, and then red is probably the strongest shaking you'll ever feel in your life. And so I'm showing in these B and C panels are the predictions at each time step throughout this earthquake. And then I'm showing the error in terms of average across the network. And so after 4 seconds, there's 2 stations that feel the earthquake, or they're seeing the earthquake. And so this black line is that first P wave, and the blue line is the S wave. And so as time goes on, the P wave travels outward from the earthquake. So we call this a beach ball, is where the earthquake starts. And so based on some initial data, the GRAPES network can then forecast shaking across the entire network, whereas Shake Alert needs to detect a magnitude, or detect the earthquake, locate it, and get a magnitude. So that takes a certain amount of time. And so if you do that, you have a slower prediction. And then if what happened in this earthquake is the Shake Alert underestimated the magnitude, and so then it underpredicted the ground motion. So the first time I applied our algorithm that was trained in Japanese data to Ridgecrest, it worked so well that I was almost shocked. And so I had to redo this a few times to make sure I was right. And so it turned out that it actually worked really well. And so it seems that it generalized well and was able to learn kind of the physics that's common to all earthquakes. And so some short conclusions on this is that I think this end-to-end learning is really important. So you don't want to specify what it should be learning in between all these steps. And so it actually learned kind of the internal representation of these seismic phases. And I think this is an important thing to show from this result. And there's this cool transfer of knowledge between Japanese and California earthquakes. So it seems like getting applied in new domains. So that's kind of the graph-based aspect I want to touch on. And then we have this is current work. The idea is to generate these time series of amplitudes from earthquakes. And so this is a project I'm working on with a lot of colleagues at the USGS. And so the setup for this problem is basically just take earthquake waveforms, turn them into I'm showing here is 5 minutes of what I'll call an amplitude time series. So you take earthquake waveform, turn it into a log amplitude. So each of these kind of peaks is an earthquake. So this is after the Ridgecrest earthquake that I showed before. So there's lots of earthquakes happening. And the idea is just take this as input, and then just predict the next sample in this time series. And so I'm going to argue is if you do this 1 trillion times, you'll learn a lot about earthquakes and the statistics and the amplitudes, and then we can hopefully start predicting or forecasting the future of these amplitude time series. So what we do is we take these pretty standard, we have 3 components of ground motion. So again, how the seismometer is moving in the east, the north, and the vertical direction. And so transformer models are usually using 1D time series. So what we do is we just extract the amplitude. So I'm taking these signals, and then you turn it into a basically log amplitude time series as we get here. And so this is the input to our transformer. And so you can see this, the first wave that arrives, you have a large jump in amplitude, and then not much jump in log amplitude space. And then as the waves recede, you have this characteristic decay, right? And so we want the transformer just to learn how one single earthquake works, and then how the relations between multiple earthquakes in time and kind of space are. And so the idea here is that you can take these amplitude time series, you can discretize them. So what I'm showing here is the velocity, so it's just the speed of the seismometer in a relative sense in centimeters per second, and then I take the log of that to get these numbers here. And just put these into a transformer, and then just predict what the next ground motion sample is. And so we're calling this guava. We had the Greg's model, so we like to call these things fruit. So guava just was a good acronym. And so the idea is you can just put these in and you predict 1 sample ahead, and then you can predict 2 samples ahead given your previous prediction, just keep on predicting into the future. And so the idea is that we'll be able to run these in hopefully real time at some point when we have enough compute. And so what we've been doing currently is, I had showed you that ridge-crest earthquake. We have a moderately small data set. So this beach ball here is the location of the ridge-crest earthquake outside of, this is about 200 miles east of Los Angeles. And so each of these, the ridge-crest earthquake, I guess, is a special earthquake because it happened in a very dense seismic network. And so each of these triangles here is a seismic sensor that was in place before the earthquake, which is important, and was sampling continuously throughout and after the earthquake. And so we took about 1 month of continuous seismic data, sampled at 10 hertz. So we get 10 seconds every sample. And so if you do that, you get about 1 billion samples or 1 billion tokens, which is, it's quite small compared to, trillion token or 10 trillion token data sets that language models use, but for an initial model, it's pretty good. And so we built just a standard llama type model, about 110 million parameters, just to take all these training data, predict next token, can train this on a desktop GPU in a few days. And so this is basically what we're doing is you take this waveform. So this is a test example, unseen earthquake. And so I'm showing here is just the P wave, again, is the first part of the first wave that arrives. So this is basically what we want to be doing in real time. And so I'm showing here is the input that we put into this guava model. So this is the P wave in amplitude space. And then we just ask the model to keep predicting the future. And so here is one kind of random generation of 500 seconds of ground motion. So a little bit weird time scale. I'm showing the log time. So this is 10 to the negative 1. So that's 0.1 seconds to about 500 seconds out here. And so what the model learns to do is predict that after an earthquake, you have some kind of fall off. That's what we call coda. And then it starts predicting aftershocks. So these are smaller earthquakes that usually happen after a large earthquake. And so in this case, there's 2, maybe 3 aftershocks. So that's what we'd expect. Here's a different example where you have multiple aftershocks. One of them is about as big as the main event. Here's a longer coda. So this is 100 seconds and then aftershock here. And then here's a different input where we have basically no aftershocks predicted. This can also happen too. You can have an earthquake and wait for an hour and then maybe there'll be an earthquake. And here's another kind of no aftershock kind of prediction. So it's all to say that this is a stochastic, it's a random process. This is what we see from language models too, but basically we've learned kind of the fundamental physics of what happens after an earthquake is you have either a fall off and then you have a certain number of aftershocks. And so this is what happens in real life. So there's this fall off in coda, and then there is two aftershocks in the first 500 seconds. So what we saw previously is it statistically matches, but it's not going to always be exact. And so that's kind of why we do earthquake forecasting rather than earthquake prediction. So short conclusions on this is that if you just do this very simple setup of take a bunch of data and predict the next sample with earthquake-like inputs, you can forecast kind of the statistics of ground motion that we'd expect. And so you don't need to do this with kind of what we standardly use, which are earthquake source parameters and an earthquake catalog. And so what we're trying to do with USGS now is how can we apply this to both earthquake early warning and forecasting of this ground motion. And so to conclude, where I think, at least for me in our group, where we think AI and earthquakes is heading is hopefully kind of combining this kind of graph-based approach of take a seismic network and embed it in a graph, get the spatial relations, and then add some kind of time series transformer model to then predict the future. And so hopefully what we can do is, what I'm showing here is what we call the shakeout. This is a simulation of an earthquake on the San Andreas Fault. And so this is showing moving north from about San Diego up to Los Angeles on the left here. So red again is strong shaking. And I'm showing here on the right is, this would be the shaking in Los Angeles from a large earthquake. And so hopefully maybe in 10 or 15 years, when we have enough computation, we can do this kind of forecasting in real time for earthquakes and get this nice predictions that we can then warn people that there's an earthquake coming or what they can expect. Kind of what we do for like a hurricane forecast. So this is where my work I think is heading, and I think it's basically just applying lots of computation and lots of data to this problem. So with that, I'll say thank you and take some questions.
Yeah. I don't know if I need. Can you hear me all right, Tim?
Yeah, I can hear you.
Oh, okay. Can you hear me? Then, thank you very much indeed, Tim. That was fantastic. That was a really super talk, and well, I certainly, for me, who's not and really knowing the machine learning type things, I found that very helpful indeed. So thank you. Hopefully, it was useful to others. Do we have any questions for Tim while we? Okay, Sophie, yes.
Do you hear me?
Yes, I can hear you.
Fantastic talk. Thank you very much. I have two small questions. The first, on the first part of the talk, I was wondering, on your graph, how did you define the edges?
Yes. So we set up the edges using the 20 nearest neighbors. And then we also included any node within 30 kilometers. That's because in Japan, they have lots of seismometers in Tokyo. So we wanted to make sure that we can get some amount of distance out. And then we use a relative edge distance. So we have one feature of the edge is just the relative distance between both nodes. And so this was important because we have a heterogeneous distribution of nodes. And so we wanted to make sure that the relative distance is encoded. We had originally inputted the absolute locations of the nodes, and that was actually a problem. Basically, the network learned that nodes that were in places near large earthquakes in the past should just predict high ground motion. And so we stopped using absolute locations because it was actually learning like the easiest thing rather than kind of the general physics of how the waves propagate between different distances.
Thanks a lot. And I had just a small other question on the second part.
Yeah.
I was wondering, in your last part, in the time series prediction, why do you never see an increase of magnitude following your?
Yeah, that's a good point. I think it's in most cases. Okay, so there's the Gutenberg-Richter scaling, I guess, is that there's 10 times as many magnitude 3 earthquakes as magnitude 4. So you're much likely for an earthquake to stop growing than for it to keep growing. And so I think the statistics are that it's most likely to stop growing than to keep growing. And so I think that's probably picking up that. So I think if I showed you a lot more generations, there would be some that keep growing. But I think statistically it's not likely to keep growing. So I think it's just predicting what the statistics have shown it. But if I showed you maybe like 10 of them, one of them would keep growing.
Thank you. Thank you. Okay. Yeah. Anyone else? Oh, go on. You knew.
In your graph neural network, you are training on some parse data, and then you are providing some instance of a new data set to predict, right?
Yes, yes. So basically what we do is we take a moving kind of slice through the earthquake through time. And so we kind of skip this, but the data we put is a 4-second time slice of the current state, put the raw data in, which is the shaking at each station. And then what we're predicting is just what's the peak shaking in the near future. So over the next 30 seconds. And so we just, every second we move forward and just input that into the training.
You are doing this in a centralized fashion, right? You need to collect all the data from stations to put into one central location. Have you thought about how this could be done in a distributed fashion? Because in practice, you will need to collect all the data, send to the GPU or whatever you're doing, and then send the warrant. Right? It would be.
So we do this because we already have this set up for the West Coast of the United States. So we have 4 different data centers that are aggregating this data every second. I haven't shown it here, but I have some work where we did tiny machine learning on little Arduino devices that have accelerometers. And so we've done this in a distributed sense too. You can basically just do predictions for that one location. It turns out that works, but you do want the spatial interactions are useful. The more data you aggregate, the better predictions you make, it turns out. So I think doing both is probably the best way to do this. Do this at a single location and use all the information you have at the same time.
Thank you.
Ben, yes.
Yeah, thanks, Tim. That was great. So as sort of a follow-on to Sophie's question, it looked like there were only a few points in your log time versus amplitude before the peak acceleration. But are you able to look for if there's any information in the run-up to the peak that might be predictive of the number of probability of aftershocks?
So you're saying before the P wave or before the
acceleration?
You so like the kind of ramp up of the P wave? Yeah. We haven't looked at it specifically, but that's definitely something we should look at. But yeah, the other idea is like, do you see something before the P wave arrives? Are there small earthquakes before that then can forecast the larger earthquakes? We haven't gotten there yet, but more analysis, I'll say that. That's what we need to do.
All right. Well, in the interest of time, we'd probably better move on. Tim, are you able to stay on the recording, or if we contact you later? Or I know you were also saying you might try and get into Boston sometime.
Yeah, I think sometime this summer. That's the plan.
Summer. Okay. So, well, let me know.
Of course.
Anyone, if you're interested, I guess, yeah, between us, stay in contact and we'll try and make sure that when Tim is here, we can let people in his room. Okay, well, thank you very much, Tim.
Hey, thank you. Thank you.
And it was super to see Theresa joining us. Great. Are you going to help with the...
Yeah, oh. Just be able to share.
Yeah, so you should just be able to share, Theresa. So there's about, what, 20 of us here from a mixture of, do we need an allow? Oh, okay.
Yes, right. Yeah, could you test your audio?
Yes. Audio is.
Hi, everyone. Can you hear
Oh,
me?
there we go. Hello there. Rachel here. Welcome. And thank you so much for joining us virtually. As I said, there's about 20 people here, and we've got a mixture of expertise from earthquake science through to machine learning, with some people in the middle. So
Wonderful. And can you see my cursor or a pointer?
yes, we can. Yes.
Oh, excellent. Okay, then I think I'm ready to go if you are.
Yeah, so Theresa again is joining us from the US GS, and you're actually in California, is that right?
That's correct.
Yes, okay. Well, welcome to the East Coast. Go ahead, thank you.
It's a pleasure to be here. Thank you so much, Rachel, for inviting me, and Brian and Rachel for hosting this event, and Catherine for helping put on this wonderful event. I'm so excited to be here to share my research on rapid earthquake magnitude estimation on fiber optic cables and strain meters via machine learning, and I'd like to thank my co-authors who are listed below. So first, I'll talk a little bit about earthquake early warning, because when dangerous shaking approaches, seconds of warning matters. Let's see here. Earthquake early warning gives valuable seconds of warning time before the shaking of an earthquake hits a populated area so that people can take cover, cars can pull over, surgeons can get scalpels out of patients, trains can slow down, and so on. We can do this because of two basic principles shown here. One is that earthquakes travel at the speed of sound, whereas information travels at the speed of light. This means that when an earthquake hits a sensor, that is a seismometer, we can beam this information to an earthquake alert center, which then gives this alert warning to a populated center, which can then warn the population through a wireless emergency alert on people's cell phones, much like when you get an Amber Alert. The second principle is that earthquakes have two main phases, a weaker P phase, which arrives first, and an S wave, which arrives second, but is much more damaging. By detecting the weaker P wave, we can give warning about the secondary S wave, which is coming later. The closer our instruments are to the epicenter of an earthquake, the more warning time we can give. Shake Alert is the earthquake early warning system on the west coast of the US and Canada. We're going to be focusing today on a region around the Mendocino Triple Junction offshore of northern Canada, which happens to be one of the most seismically active regions in North America. We'll also be discussing distributed acoustic sensing seismology, or DAS seismology, which is the use of fiber optic cables to measure strain with high spatial and temporal resolution across long distances. In this study, we used 2 years of data from a 15-kilometer long cable onshore from the Mendocino Triple Junction, including a record of a magnitude 7 earthquake which occurred offshore Cape Mendocino, shown here. And here's the record of that earthquake. We can just barely see a P wave arrival occurring here, with the much stronger S wave arrival occurring right after it. Although our cable, this red squiggly line on the left here, is onshore, there are offshore cables in this region which we hope someday to use for monitoring to improve warning times for offshore events like the magnitude 7. In fact, there are plenty of submarine cables across the world's coastlines shown in this map here. These are very approximate cable locations, and they are crossing subduction zones such as the Cascadia subduction zone, which is offshore Oregon, Washington, and Western Canada, and offshore Alaska. These are some of the world's most seismically hazardous regions. We seismologists are actively working to gain access to these cables for offshore monitoring efforts to improve earthquake early warning capabilities. These cables go typically where typical seismometers don't go because it is too expensive to deploy, maintain, and continuously monitor data from deep water seismometers. Another reason to use DAS is that it measures what seismometers don't, which is strain. Seismometers typically measure acceleration, velocity, or displacement. This figure shows how strain meters can capture low-frequency signals, which are important for some of the largest and most damaging earthquakes. Low-frequency signals are created by large magnitude earthquakes because their ruptures are longer and thus create longer period signals. And so in these figures here, we can see the first arrival, that is the P wave. In this borehole strain meter data, this is not DAS, we can see this low frequency energy occurring right after the P wave, whereas this seismometer, which is recording acceleration, which has then been numerically integrated to velocity, we're missing that low frequency energy. And so in an earthquake early warning context, we really want that energy to tell us when a P wave has occurred as soon as possible. And so this brings us to our motivation and our goals for today. We want to use distributed acoustic sensing because it offers new opportunities for earthquake early warning, in that DAS uses fiber optic cables, which are located both on and offshore, and it measures strain, which can capture low frequency near field terms. Near field terms are just the kind of signals that we can measure near the earthquake, which are characteristic of large magnitude earthquakes. And so our goal for today is to predict, is the earthquake magnitude greater than or equal to 5.4? That is it a moderate to large magnitude earthquake versus a small earthquake from the first 4 seconds of waveform after the P wave arrival, without calculating the hypocentral distance from the strain waveform statistical features. Hypocentral distance is just the distance from where the earthquake occurs to the sensor. Now, again, our cable is 15 kilometers long. The sensors are separated by 5 meters, so there's about 3,000 channels recording waveforms. And we need to pick P waves quickly and accurately on thousands of channels, which is very difficult. And so we use an algorithm called PhaseNet DAS, which was released in 2023 by Tu et al. In Nature Communications. So because this is a machine learning kind of workshop, we're going to talk a little bit about this model. It's a deep learning model for picking P and S phase arrivals on DAS data. There was a previous model called PhaseNet, which was just picking on individual waveforms. And so we can see what's called a waterfall plot here. This is time on the y-axis and all of the channels on the x-axis. And we can see the weaker P wave arrival coming in first, followed by the S wave arrival. Now, PhaseNet would just pick these individually, just like doing it on a typical seismometer, but we can see these picks are rather messy. There's a lot of scatter there. So they use a Gaussian mixture model to clean up those picks, and we can see they look much neater here. And so they use that for training data for the next iteration. And then those picks get cleaner and cleaner until you get a much nicer model, which is PhaseNet DAS. On the right-hand figure here, we can see some of our own data, and we can see how these PhaseNet DAS picks are much cleaner. They're picking the P wave very nicely. And so this is how we pick our P waves for our study here. So our DAS data set looks like this. We've got 2 years of data. We're picking only earthquakes within 100 kilometers of the DAS cable. We've got 25 earthquakes between magnitude 3.5 and magnitude 5.4. We actually have also the magnitude 7 earthquake here. We can see a bar plot showing magnitude by the number of earthquakes. We actually have more magnitude 3.5 earthquakes in the catalog, but because they're smaller, they're noisier, and it was difficult to pick the P waves on them, so there's less magnitude 3.5s in our working catalog. And we can see here there's very few large magnitude earthquakes. That's due to the relatively short time frame, just 2 years. Large magnitude earthquakes don't occur all that frequently. That's true for our data set. That's true for DAS data sets in general, because DAS is a fairly new type of instrumentation. And so to get more data, we supplement ours with borehole strain meter data, seen here. So we're looking now at 3 different regions: Mendocino Triple Junction, Napa Valley, and Ridgecrest. Now we've got 452 rather than 25 earthquakes within 100 kilometers of each of the 7 strain meters shown here. We've got 35 magnitude 5 or greater earthquakes, so a much more robust data set. And we've got 1,949 waveforms. So much larger data set, which is good because we need a large data set on which to do machine learning. Here's a schematic of a borehole strain meter. They're encased in cement, which is about 100 meters below ground. So they're very well coupled to the Earth, which means they're getting very good data. So again, our method is to predict, is the earthquake magnitude greater than or equal to 5.4 from the first 4 seconds of the waveform arrival on strain waveforms without calculating a hypocentral distance. So first we're going to calculate some features of these borehole strain meter waveforms. Then we're going to do some machine learning on those features using XGBoost. And then based on those borehole strain meter results, we're going to analyze select features of the DAS waveform. One of the most important features that we're going to be analyzing is continuous wavelet transforms. Now, these are kind of like spectrograms, but instead of using sines and cosines, we can use different families of wavelets. Here's some examples shown here. And so we've got a earthquake waveform shown in black here. Then we've got one of these wavelet families shown in red here. And we translate this across the earthquake waveform at increasing scale. So we're just kind of stretching it out and integrate over the two. And from this, we get a scalegram, which is period over time. So again, kind of like a spectrogram where it's period or frequency over time. Now, what's different between a continuous wavelet transform and a spectrogram, other than the fact that we can use different wavelet families, other than just sines and cosines, is that this has adaptive resolution, meaning that at lower frequencies we have higher frequency resolution, and at higher frequencies we have better time resolution. And so that when we have a dynamic waveform, that means we can get more better resolution, better capturing this waveform better as it's changing through time. Earthquakes, of course, do change through time, and so we're better to reproduce this waveform. And so this is why we choose to use continuous wavelet transforms rather than spectrograms for our purposes. Here's an example of a continuous wavelet transform feature. We're using 3 different frequency bands, 0.2 to 0.5 hertz, which is shown below, 0.5 to 2 hertz, and 2 to 5 hertz. So on the left-hand side, we have 2 earthquake waveforms, a large earthquake, which is shown in blue, and a small earthquake, which is shown in red. The top row is the large earthquake, and the bottom row is the small earthquake. This is in the lowest frequency band, so 0.2 to 0.5 hertz. And these are all continuous wavelet scalograms. There's 7 seconds shown here. Each of these windows is 4 seconds with 3-second overlap. So 7 to 11 seconds, 8 to 12 seconds, so on and so forth. The P wave pick is shown in this cyan line here. And so we can see that for the larger earthquake, there's a lot more low frequency energy than in the smaller earthquake. In order to get a feature, we take the median of this entire scalegram here. And so we can imagine the median is lower here, gets higher, 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 and we create a time series out of that. So it would kind of swoop upward here. And in this one, it would have much less dynamic range. From this time series, we calculate some scalar features, the maximum, the median, minimum, and the range. And we do the same for this one. And so that's how we get our scalar features that we then input into the machine learning algorithm. And we do it for 0.2 to 0.5 hertz and et cetera, et cetera. We do it for different wavelet features, wavelet families rather. And we also take some strain features like peak-to-peak amplitude. And so this is our suite of features that we then use for our machine learning algorithm. And so these are 2 example features that I've just plotted on a 2D diagram. We've got, like I said before, 1949 waveforms. So there's 1949 data points here from different stations, channels, earthquakes. And I've colored them by magnitude from 3.5 to 7.1 magnitude units. And we can see that not only are these two features correlating well between each other, they're also correlating quite well on the magnitude scale. And so that the higher the continuous wavelet transform power is, it's also a higher magnitude. And so our threshold for that we're using for today is magnitude 5.4. So that's kind of this teal color here or higher. And ideally, we could draw some decision boundaries where if we got a new earthquake in and it landed, say, in this quadrant, we would be able to decide, okay, it's greater than or equal to magnitude 5.4 because it's teal or hotter. Now, of course, these are real data, and so there's a lot of scatter. It's hard to decide exactly where these decision boundaries should be, and we probably shouldn't be doing it by eye anyway. And of course, there's more than two features. There's actually 127 features that we're using. And so this is what motivates us to use machine learning in order to get the best decision boundaries based on our data set. And we do this using a decision tree is a fairly reasonable model to choose for drawing decision boundaries. These decision trees work like this. We've got a magnitude, we've got one feature that we choose randomly as well as a value for that feature. We take a random subset of our waveforms, in this case 682, and we decide based on this feature and value which one are positive or negative based on this Boolean. So there's 656 these 682 that have a this is kind of cryptic, but this feature is less than this value and 26 where this feature are greater than this value. Then for that, we calculate a Gini score, which is 1 minus 656 over 682 squared plus 26 over 682 squared. That's P is a proportion of the subset that belong to class I in the subset. Sorry, I can't see that word. There's something covering it. And so we get a Gini score of 0.073. A Gini score closer to 0 means that this is a perfectly classified node, meaning that all of the values would be in one class or another. So this is pretty close to 0 because 26 is fairly close to 0 compared to 656. And so once the Gini score reaches 0, then we terminate that branch. It's called a leaf node, or you can also decide just as a user decision that we only want, say, 3 or 4 layers in our tree so that we don't make this tree too complicated so that it's still generalizable for other data sets. And so we keep on going, say we take this 26 and take a random subset of that. Again, take a feature, take a value, and just do the same thing until we get a Gini score of 0 or we reach our predetermined depth. And so that's how a decision tree works. At the very end, we get some probability of the class being either greater than or equal to 5.4 or less than or equal to 5.4. And XGBoost is just a sequence of these decision trees. It's optimized by gradient boosting. It's sequential decision trees where each of the trees learns from the errors of the previous tree in order to improve its tree. There's regularization to avoid overfitting or bias. So again, none of these trees can get too complicated in order to remain generalizable for unseen data. And it prunes poor performing branches so that if, say, in this branch, the Gini scores are all really high, it'll just remove that branch so that it won't be included in the next tree. We also use SHAP scores, so Shapley additive explanations. This explains that for each feature explains how each feature contributed to the prediction for a specific branch with Gini scores, and it aggregates the contributions across all branches/trees to determine the most important feature overall. So we'll see some plots like this where the most important features are ranked from highest to lowest. And so we start out with 127 features. We whittle that down to 56 features by having only those with the absolute correlation of 0.35 or higher to the target feature, which is the earthquake magnitude greater than or equal to 5.4. We do put these into XGBoost for 50 model runs just to see which are the top features. And we get top 6 features based on a kind of drop off after 6 features. We take those 6 features, put them into XGBoost for 500 model runs, and from this we get our final prediction. Here we see some confusion matrices, and so the way we read these, there's a true label on the y-axis and a predicted label on the x-axis. And so for these, there's say 127 on average for these 500 model runs. Earthquakes that are less than magnitude 5.4, and there are 27 earthquakes that are greater than or equal to magnitude 5.4. And yet we estimated, or we predicted that there were about 28 greater than or equal to magnitude 5.4. And so we're over predicting a little bit. And so of all of this is recall, which means that of all of the earthquakes that are actually magnitude greater than or equal to 5.4, we predicted 82% of them. And of all of our predictions, 77% were correct. Now these are fairly good numbers, a precision of 77, recall of 0.82 for machine learning. These are okay. Of course, they could be better. But then we compare them to the Shake Alert, that is the current operational system for earthquake early warning. For these, there's 52 magnitude less than 5.4 earthquakes and 3 magnitude greater than or equal to 5.4 earthquakes. And yet Shake Alert predicted that there were 10 magnitude 5.4 or greater earthquakes. And so although they correctly predicted 100% of the magnitude 5.4 earthquakes that occurred, of their predictions, only 30% were correct, whereas of our predictions, 77% were correct. And so, again, these are promising results for earthquake early warning, given that there's no location information, only one station, and only 4 seconds of earthquake data. We have higher precision results, which reduces the possibility of false alarms. And our method is totally independent from existing operational systems. It's a completely unique method from what's being used right now. Some important caveats is that these are from Shake Alert's maximum magnitude estimations after 2 seconds of waveforms. Ours are after 4 seconds. So it's not really a fair comparison, but just an interesting comparison. Our method is not intended to replace Shake Alert whatsoever, but rather to supplement it in offshore areas, especially for subduction zone scenarios where locations are difficult to ascertain quickly, e.g. Cascadia and Alaska. So just a couple more slides here. We've got top 3 features using our SHAP score. So we're looking at the top 6 features again. And we note that the top 3 features are in the lowest 0.2 to 0.5 frequency bands. So again, 0.2 to 0.5 hertz, 0.2 to 0.5 hertz, 0.2 to 0.5 hertz. The maximum strain doesn't come in until the 6th feature. And this is interesting because the maximum waveform amplitude is a typical feature used in the current operational earthquake early warning system. And so it could be that earthquake early warning systems used today could benefit from using more frequency-based information, and especially those in the low frequency bands. This is actually not new information. Why does the low frequency feature work? Well, larger earthquakes have larger ruptures. They're rupturing a much larger part of the earth, which means they're emitting longer period waveforms compared to smaller earthquakes. This is very old theory and information. So I'm showing this slide again. These are actually the same channel of the DAS fiber from 2 different earthquakes. So again, this is strain information that is able to capture this low frequency signal, and we can see just how much more long wave length, that is long period information, that this magnitude 7 earthquake has compared to the magnitude 4.8. That is, keeping in mind that the 4.8 is much closer and has less attenuation. But even so, it's clear that there's much more long period information in the magnitude 7. So this is for those of you who are earthquake scientists, maybe you remember the tau p feature. And so this is kind of an older theory, an older kind of idea that kind of came and went. But back then they didn't have so much strain information, so many strain meters, and certainly not DAS. So this is a theory that may want to be revisited. And so finally, we use the models trained on the borehole strain meter data to actually predict on the DAS data and the borehole strain meter for the Mendocino Triple Junction magnitude 7 earthquake, and found that for the DAS data, it correctly predicted that it was a magnitude 5.4 or larger earthquake 91% of the time and 100% of the time for the borehole strain meter data, showing that this model is very accurate for predicting large earthquakes. Even though it was trained on borehole strain meter data, it does work for DAS data as well. And we put the DAS data just superimposed on the borehole strain meter data. And there is a systematic offset, which we presume is due to burial conditions because the DAS is under loosely consolidated sediments, and the borehole strain meter is cemented 100 meters underground. The DAS is fairly shallow, and also they're different instruments. So that's kind of what we presume that offset is due to. And so in conclusion, we apply machine learning to discover features that can discern large from small earthquakes within the first 4 seconds of borehole strain meter waveforms, and successfully applied this model to predict that DAS waveforms came from a large earthquake. We found that continuous wavelet transform powers filtered in low frequencies proved to be the most effective for these predictions. They were capturing low frequency signals in near field terms of large earthquakes due to large ruptures of earthquakes we predict. We found that success metrics of our model were in the ballpark of operational systems, and we explored DAS applications for earthquake early warning. And these are especially important for subduction zone scenarios in Cascadia and Alaska. And so again, I'd like to thank the organizers and thank you for having me. And if you have any questions, I'd be happy to take them here or offline. My email is in the upper right, and you can contact me anytime. So thank you so much.
Very much, Theresa. That was great. Yeah. Do we have any questions for Theresa? Yes, Mostafa, go ahead. Welcome.
Thank you for the talk. Very interesting results. Could you tell us the difference between top 3 features that you said were the most important features?
Sure. Yeah, let me just share my screen again, actually. So they're different wavelet families, and they're different. Oh, let me get up there. And they're different. Yeah, I think that's it. They're different wavelet families. So the third order Gaussian, first order Gaussian, and the Morlet wavelet that is centered on 1.5 hertz. And so I have them all here, first order, third order, and the Morlet wavelet centered on 1.5 hertz. And so they're, especially the first order and the third order, we would find that they have like a lot of similarity. So there's a lot of correlation between the first and third order. What we find especially interesting about the third order and the first order Gaussian wavelets is that they actually look like a first arrival of a P wave. And so it's almost like a matched filter kind of like a template matching as we translate them over over an earthquake waveform. And so it makes sense that they have a lot of power as we, for an earthquake. And yeah, like.
And it's narrower and probably low frequency won't have that artifact, like corner artifact. But then in terms of the frequency range, they all were same narrow band of 0.2 to 0.5, right?
Yeah.
And the measurement was exactly the same maximum.
Yeah.
And then second question, did you include by any chance any sort of like epicentral or depth feature into your inputs?
No, in fact, we did that on purpose because one of the greatest uncertainties for offshore earthquakes is location. And so we wanted our features to be free of location information. And so it really is just, other than the fact that they are within 100 kilometers, there's no information location. And the fact that they are within 100 kilometers is also by design because our detector on DAS is fairly good at not detecting teleseismic earthquakes. And so it really just detects local and regional
It was
earthquakes.
by design choice, but just for the sake of research, because we know that both distance and depth affect the frequency content, right? So it would be interesting to just test that if you put the ground truth, these two features added to the whole feature mix, if it can change the results or not, that confirm this well-known fact from seismology, right?
Yeah, that's an interesting point. No, we haven't tried that.
Thanks. Just curious.
Yeah, thank you.
Go on, Hillary.
Hi, Theresa, thank you for the nice talk. So do you consider the data saturation of DAS, because sometimes the amplitude can get so do you consider that in your model, or you just let the model to figure it out by itself?
Right. DAS saturation is one of the outstanding challenges because if the DAS cable happens to be too close to a large earthquake, that's a challenge for any kind of earthquake early warning using DAS. And so one of the ideas we've had is to try to encode saturation into the machine learning model, where if it's saturated, we'll know that it's a large earthquake and something to be alerted for. And then there's also, of course, like Martijn van den Ende has his code, or has like a paper on how to unwrap the saturated phase. And so we could kind of, in some cases, reconstruct the saturated phase waveform. But so far, that's just something that we've talked about and thought about, but not much more than that. So yeah, that's kind of the two ways that we've talked about approaching that, is encoding saturation in as a feature that we could then train the model, possibly on synthetics to recognize that as a large earthquake, or trying to fix it essentially by unwrapping the phase wrapped waveform.
Thank you. Janusz, did you want?
Yes, I have just a question about to clarify something. In your wavelet transform, you're using 3 frequency ranges. This is due to the different dilations applied to individual mother wavelets, so that you form a basis that captures different frequencies. I wasn't quite sure I understood, how did you get the 3 frequency ranges for a specific mother wavelet?
Oh, it's more like, let me get up here. We allow the wavelet transform to go through all of its scales. So it's not like we're constricting any kind of periodicity or period. We're not constricting any of the periods in the wavelet transform itself. It's once
What do you mean by scale? What is the definition of scale?
Meaning the stretching of the waveform.
It's called dilation. Okay, yeah, okay.
Oh, the dilation. Thank you. Yes. So the scaleogram is allowed to go through all of its periods. And then basically once we get a final scaleogram, so once it looks like this, then we just truncate it. We just filter it afterwards. So we would get, oh, sorry, you can't see my hand.
And how many scales are you using?
200.
Okay,
Thank you.
Sure.
great. Thanks. Sherry, did you have a quick question and then we'd better shut?
So that was a fantastic talk, and thank you for that. So I was wondering, so since it seems that this method is inherently based on the truth that large earthquakes are different at the start than small earthquakes regarding their frequency contents. So was wondering, since you show a clear example that the small earthquake have a higher frequency content, is it possible if that there are other features that changing the frequency content signal of the earthquake might disturb your result? Like, let's see if you have different attenuations in the path, or if you have kappas in your site, might disturb your result.
Right. Attenuation is definitely important. Yeah, so the one thing that attenuation, like in this example, we can say that the larger waveform was attenuated of high frequency, but the smaller waveform having more high frequency doesn't mean that it's going to have a lot more low frequency. Like, you can't add this long period signal to the smaller waveform just through path effects, if that makes sense. And so there is something to be said about just the innate rupture process, adding these really long period components. And it's not just the frequency that we're looking at, because we are using all 6 features. I guess I didn't mention this, but we do have a constraint on our decision tree that all 6 features are on our XGBoost, that all 6 features are used in every tree. And so the maximum strain does need to be taken into account. And so the smaller earthquakes won't have that strain feature as well. And so in this example, we can also see that there's a factor of 2 or 3 more amplitude for the larger earthquake rather than the smaller earthquake, even though it's much farther away. And so, yeah.
This point slightly and say one thing that I think we also need to remember for the non-seismologists in the room is how long an earthquake actually lasts. So, I mean, you're showing here 4 seconds of waveform, but a magnitude 5 earthquake is only going to last a second or so. So, that earthquake is done. And even a magnitude 7, how long does a magnitude 7 last for? I guess that's probably more like 10 or 20 seconds. So that's probably, we're looking at sort of half the rupture, potentially half the rupture of that earthquake. So when you're sort of trying to say, what's happening right at the beginning, you have to remember, is it actually the beginning of the earthquake, or have we actually had most of the earthquake? It's just the beginning of the waveform that we're getting. Thanks.
Mm-hmm. Yeah, that's a good point. You're right.
Okay.
Anything else or ready to? Okay. Well, thank you really very much, Theresa. Thanks for the introduction, because the DAX especially is really transforming. You're using a new technology and a new data type in what you're doing. So it's, I mean, I have some curiosity as to how much your results depend on the new methods versus the new data type, but that's a longer story.
Well, thank you so much for having me. Take care.
So I think now, I hope you can stay with us a bit, Theresa, and I know I want to talk with you on Zoom at some point before too long. I'm sure you're willing to be, as you said, your email address is there, so please reach out if you want with Theresa. Hopefully we can get you to visit in person at some point someday. So we're now sort of changing gears slightly, because we've got Brian and I think Janusz as well, are both going to come up and tell us something about the work they've been doing in this sort of 1-year preliminary, exploratory award that we've had through the Hariri Centre. So this is, come on and start. Really, this is learning how to take what you've learned from other fields and try and apply it to a text.
Let's see if I can figure out. Okay, I think we got it. All right. So my name is Brian Kulis, and I'm just gonna talk for like 10 minutes. I'm involved in the focused research program that we've been running at BU through the Hariri Institute, and so we didn't want to spend too much time talking about kind of what we've been doing, but we thought, some of you might be curious about the stuff we've been looking at BU, kind of why, basically why we're all here. So this is work that's mainly being done by David Liu, who's my PhD student in the back there. He is working on this, and we're collaborating with Chris Johnson, who's at Los Alamos, and Laura Laurenti, who's a postdoc at ETH Zurich. And Rachel has been instrumental in also helping us sort of understand earthquakes. I'm not an earthquake person at all, and so I've actually learned a lot over the last year about earthquakes. My background is in machine learning, and over the last few years, I've actually been working in audio. So I spent maybe the last, 7 years or so focusing a lot on audio types of problems. I spent several years actually splitting my time between VU and Amazon, where I actually worked on Alexa and worked on some of the speech recognition pipeline for Alexa. And then also over the last few years, I've been working on AI for music, which again is an audio domain. So my interest in earthquakes started about 1.5 years ago when we hosted another workshop at BU through the CISE Center, and I started talking to several people about machine learning for earthquakes. And one of the conversations I had was with Chris Johnson, where I just sort of said, when we're doing a bunch of stuff in audio, I wonder how effective some of these models would be for earthquake data, for seismic data. And so we started kind of working on a project together, and then started this focused research project. So the high-level motivation here is if we look at foundation models for sequence data, whether that's audio, text, seismic data, what have you, a lot of that's been dominated by transformer architectures. So in fact, you know, in Tim's talk earlier today, he talked about using a transformer model for seismic data for things like, you know, early warning. And so a lot of these foundation models are based on transformers. If you look at ChatGPT or vision transformers, all sorts of generative AI applications, they're using transformer architectures. Now, in the audio community, transformers are actually not used as heavily for those models, largely because if you work with raw audio, those are very long sequences. For example, if you're dealing with like, you know, 44.1 kilohertz audio, that's 44,000, you know, time steps per second. And so things like self-attention, which is what transformers use, though, that doesn't scale well to long sequences. And so an alternative that people have been looking at recently is something called state space models, which some of you may be familiar with. They are an alternative which do not scale quadratically and were actually developed initially with audio in mind. So the idea was to try to take some of the ideas from state space models and apply it to seismic data, and that's what we've been doing over the last year. I want to stress, by the way, that this is very preliminary, so we're still kind of doing this. We're still fairly early on in it. I'll give you like the 2 or 3 minute overview of state space models. It actually dates back to sort of modern state space models like Mamba and others. They date back to work from Albert Gu, who's a faculty member at Carnegie Mellon, and some of his colleagues. He wrote a paper several years ago now called HIPPO, which stands for higher order polynomial projection operators. And basically it's a framework for how to take a long sequence and project it, compress it down in a way that sort of saves as much information, remembers as much about that sequence as possible. And so it projects it down into some sort of higher order polynomial. And underlying the analysis of this kind of model is a type of differential equation or state space model. It's a continuous time state space model where you have the input time series, which is U, you have some sort of compressed representation, which is X, and then you have some kind of output or prediction, which is Y. And you can develop this kind of continuous time state space model, discretize it, and then use that to actually come up with ways to optimally compress a long sequence so that you remember as much as you can from it. And so the state space model sort of is derived from this kind of framework. It was then put into a neural network in follow-up work. There's a model called S4, and I'm not going to go through this in any detail, but basically in HIPPO, these A, B, C, D these matrices are fixed. They're kind of, you can compute them directly. And in this S4 model, you actually parameterize them. You initialize them using HIPPO, and then you kind of learn on top of them. And so you end up building a model where you have an input sequence, and then you have some sort of state space model, and you have an output sequence. And the state space model is learned by the parameters here, A, B, C, and D of your state space model. That was further developed recently in a model now, which has become very popular, which is called Mamba, which basically takes S4 and goes a couple of steps forward beyond S4, where it does a bunch of things like this selection mechanism, it also has a better way to utilize the sort of GPU for training, and that results in a type of model that's actually become very effective for audio problems and even language problems where you have very long sequences of data. So you have Mamba architecture, which I'm not going to go through in any detail, that is hardware aware, so it can utilize sort of the GPU very efficiently. And so why is this a powerful model? Well, one reason is that empirically it works very well. So this is something actually David did recently, where we applied a pretty standard kind of Mamba type architecture. It has a bunch of Mamba blocks in it. And we applied this on audio spectrograms in this case to the problem of predicting things about music. So this was applied to music. And so we built this model, we called it MoMamba for music-oriented Mamba, and we looked at key estimation, genre classification, meter detection. These are benchmark kind of problems in music, audio, raw audio for music. And it does very well, actually beats the state of the art on all of these tasks. So it's a very powerful model. You can use it almost out of the box. So we have been building a Mamba type architecture over the last year or so. It's an encoder decoder model. So it takes seismic data, it encodes it, compresses it down, and then it uncompresses it back to the original time series. So it tries to reconstruct after it's compressed. And the idea is eventually, if we train this on a large enough amount of data, we can use these compressed data representations or these features that are learned by this model for various downstream tasks, whatever they may be. We haven't done that yet, but that's the kind of long-term goal. So we've trained several Mamba models on seismic data. I'll show you one model that we've been working on recently. This is trained on STED, which is, I guess, a standard data set in the community. It has like almost 3 million samples. We look at every sample with 6,000 time steps where the sample rate is 100 hertz. We include, when we're training, both earthquakes as well as noise. We split 80-10-10. We build off of an architecture that was done previously by Chris Johnson, which was an architecture that did not use state space models, but used a very large foundational audio model. So we used many of the same loss functions to train that they had. We have, anyway, a number of different parameters and so on. We can compress down, when we get to the encoded space, it compresses it by about 67%. So what happens when you apply this is, if you look at these raw waveforms, these are the 3 channels here. Actually, you can't see this very well necessarily, but we have kind of blue and brown or orange corresponding to the waveform before we've compressed and then after we've compressed it and uncompressed. And they're matching very, very well. So it's compressing down and reconstructing almost exactly, at least when you look at the raw waveform. When you look at the spectra, in some cases, like in this particular example, at the high frequencies, there's some mismatch there. Also a little bit at the low frequencies, but most of the reconstruction is actually done pretty effectively. So this suggests that the model's actually working, that it's actually doing something reasonable. Okay? And we know that the losses are going down, the train losses, the validation losses are going down. So so we have a model now. We're still tuning it, we're tweaking it, and then hopefully at some point what we want to do, and part of the reason we want to talk to, people who work in earthquakes, is we want to be able to use this for some kind of downstream task. And we, of course, need to do a lot of other things too, like we need to compare this to other models, like the models that, for example, Chris Johnson has already built, and other kinds of transformer-based architectures and other things. So I think the long-term vision here is we do want to hopefully build some kind of foundational model on a lot of different data. We think that because of Mamba's sort of effectiveness on long sequences, this might be a good candidate for such a model. It's also a fairly low parameter compared to like a transformer-based model. So it's actually quite efficient. And so hopefully we can kind of keep working on this and find some good applications of this type of model. So be happy to talk to people further about this throughout the day. But that's it for me. Thank you. Thank you very much.
Thank you. Do you want to just go straight on to Janusz?
Yeah, we can go. Well, either way, I don't know, whatever.
Can I ask a question?
Yeah.
Yeah, sure. That way.
Have you thought about applying to DAS data?
So no, well, not until 2 minutes ago. But yeah, no, I mean, I wasn't. No, I didn't. And so, does that seem like a reasonable thing to do?
That's an important thing
So.
because when you talk with people who are supporting the data storage for seismic data,
Yeah.
and they can do. They said, I mean, for seismic data, there's not big issue, but DAS they couldn't touch because it generates so much data.
Hmm.
So I think if your model could, cut off the storage side by 6-7% or more, that makes DAS like the data less intimidating to store and process. So it's
possible.
It's yeah.
Yeah, I think that's possible. For the moment, we've been looking at this kind of seismic data, but yeah, certainly.
Yeah, that's true, because one of the problems of DAS is just the sheer
The amount of data,
volume
yeah.
of data. Yeah.
And this is what they use actually for compressive DAS. They do this autoencoder architecture, and then they use the bottleneck that the compressed feature that is extracted by the network at the middle, and then they use this encoder later as a decoder later to reconstruct whenever they want to access data. And this is kind of the start of this is happening in DAS community.
So what's their encoder, decoder? Is it using a
They use different. They use much simpler like CNN.
CNN or something? Okay, interesting. Yeah, so this would be a candidate.
Yeah, go on then, Sherry.
So I have a pretty maybe naive question for the model is what is this framework trying to predict?
So the way that we're training this is we are it's trained in a essentially self-supervised manner. So it's taking waveforms, it's compressing it, it's uncompressing it, it's trying to reconstruct. So the loss function here is just looking at the reconstruction. There's a few different reconstruction errors we're looking at, like we have I think the raw waveform, like L1, L2 reconstruction error. I think there's an FFT loss. So it's really just looking at reconstruction of the waveform.
So Brian, would one way of thinking about it be compared to what Tim was talking about in his Guava algorithm, where he was looking at the features that were coming out? In a way, you're trying to find something of a similar nature.
Yeah, it's very similar to what Tim talked about, although Tim's training it differently because he's training it for he's training it to predict the next time step.
Yeah.
And we're just training it as a reconstruction. So it's set up a little bit differently.
Right.
But it's a similar goal, I think.
Because as someone like myself who's interested in earthquake sources and a better understanding of the earthquakes themselves, often what we do with large quantities of data is try and parameterize it, in relatively simple models. And we know that we are losing an awful lot of information when we do that. So I'm actually just curious to see what are the features that are coming out as being the important things in Guava, in what you're doing. And see whether we can then use those to help us understand what to look at in more detail, to learn more about the Earth and the earthquake impact on it and the earthquake themselves.
Yeah, and we haven't looked at that. And
I realize that would be the next sort of stage, but yeah. So I'm quite curious what these features are. Ben.
Just wondering if that information loss at high frequency, is that something that is set by some parameter choice, or is that something that is intrinsic to the way that you're shedding information for compression?
Yeah, that's a good question. And I think Chris, when I we were talking to Chris last week about this, he had some thoughts about it. I don't know, David, do you remember?
I think he said the differences in the kind of the middle area of the spectra had more to do with like the differences of the magnitude and the wavelengths. So he said if we focus on that area, then we can kind of ignore the super high frequencies for now. Then the reconstruction might be better.
So it sounds like it's a choice of parameters a little bit, yeah.
Okay. So yeah, I think we're still trying to figure that out too.
I think in the interest of time, we'd better move on and let Janusz have a few minutes before we break.
Okay. My name is Janusz Konrad. I am from ECE here at BU. And this is very preliminary work we did over the last 6, maybe 8 months with my colleague, Professor Ishwar, who is at the back, and our master student. So this is very preliminary work. There's no AI in it. There's no machine learning. One day maybe, but this is kind of an idea that we had some months ago. So EW systems have been developed in the US and Taiwan and Mexico, Japan, and so on, under construction in many other countries. The issue is that they are quite costly to deploy, costly to maintain, and so on. So we had a crazy idea, cameras. So I'm a camera guy, and I've been working with camera on my scientific life. And cameras are everywhere, as you know, well aware. Any camera here? Probably somewhere. Yeah, here, right here. So cameras are everywhere, and they are in cities, along highways, transportation hubs, elevators everywhere. And they're owned by local governments, law enforcement, national agencies, and so on. And the idea is, can we somehow use this sensing capacity of millions of cameras in the world to somehow do EW? And the idea is this, that here we have a very grainy, low quality, but a video from an earthquake in China, which camera starts to shake. And this is not seismometer. This is not a fiber being squeezed, but this is a camera and does something, right? It could be equally well a truck rolling by, but it could be an earthquake. So the idea is basically they have a camera looking at the scene, and a few assumptions that we need to make. One is fairly long distance. It's not looking like, half a meter at the wall. Typically, surveillance cameras are looking at the scene. Secondly, there should be only horizontal or vertical movements. So the issue is that when the camera rotates, it's a bit problematic. But cameras typically are rigidly mounted, not all of them. And I'll show examples to the contrary too. And in this case, you're recording a set of frames, video frames, and they will shake. And can you infer a vibration from those video feeds? Only slight with formulas. The main idea is if the camera, if the frames shake, there will be translation, displacement between frames, and how to estimate it. You can do correlation, very expensive computation. There's a method called phase correlation, well known in the video coding community, that basically takes Fourier transform, DCFT is discrete space Fourier transform of a frame, and produces this I hat, and omega being frequency. So this is basically Fourier transform of a single frame. Now there's this magical formula where you can take multiplication of those Fourier transforms, one of them being conjugated, and then normalized and inverse Fourier transform. This produces this R function, which ideally, if the two frames are simply shifts of each other, this will be a pulse at location of the displacement. So you just identify and you know how much they displace. That's ideal. In reality, this will be a surface, and you need to find the maximum of the surface, which algorithmically is also doable. So this displacement basically gives you X shift and Y shift. That's all math. Now, we applied this. Here is a New Jersey earthquake from a year ago. This is all harvested from YouTube. And this here is basically, you will see quality is not great. I start shaking, somebody's backyard. And we applied our algorithm frame pair by frame pair, and we obtained this kind of waveform. The red one is the vertical shift. There's very little horizontal shift. And frequencies, if you do a spectrum analysis, this will be roughly like 4.5 hertz, reasonable frequency of the waveform. What we did, we measured the energy stored in the waveform over a 2-second window, and it kind of a rise and fall. This could serve as a trigger. Yeah, there's an earthquake, or there's a vibration going on. Another earthquake from Dalian, China, 3 years ago. More problematic because camera is kind of not rigidly mounted. There will be some translations and a bit of rotations. Again, we applied the algorithm, we get both significant X shift and Y shift, reasonable frequency range, and here's energy window going up, and basically on the rise, we could say something's going on. And the third example, this is Wenchuan in China, 15 years ago or so. This is more complex video because, as you will see, buses are going by, people are walking, typical surveillance scenario. A camera shakes. It's not as strong, working only 4.6. And in this case, we also can estimate the vibrations, and they look like this: significant vertical, very small horizontal range, about 5 hertz spectrum. And again, energy goes up and then goes down. These are 3 examples. So this is the first part of the talk. Now, what we conclude from here is that estimating vibrations from video feeds is feasible. Now, the Fourier transform can be implemented for those not in earthquake community, maybe, is something called FFT, very fast implementation. It's in some way, it's supported on modern cameras because coding uses something called DCT, can be used for the same purpose. So modern cameras can actually perform this computation if you modify the firmware, if you apply some extra algorithm. And rise in vibration energy is basically a trigger for saying, yeah, something's going on here. So now, the downside is, of course, that you have cameras in the city or in the rural area, and there's a tractor going by or something and starts vibrating. So there will be errors. The upside is that there's, in a metropolitan area like Boston, there's literally tens of thousands of them everywhere. So could it be useful for EEW? Well, we wanted to test it. Well, we don't have earthquakes with 50,000 cameras recording earthquake, so we need to cheat a little bit. So what we're going to do, we are going to use seismic data, and we are going to inject errors that are kind of typical of what would happen with a camera. Our approach is naive, so please don't kill me. We did something extremely simple. We are not earth scientists, but we did something that we felt want to have full control over. We didn't want to use a black box and we don't know what it's doing. So we did everything from scratch, as engineers typically do. So we took, thanks to Rachel and her student, thank you very much. That was extremely useful. This is Oklahoma 2016, very nice data set that our student used. There's about 1,800 stations. Epicenter is quite low, right here, something to remember. And we use this data set to run our very simplistic experiments. So first of all, we use something simple called STA-LTA. Everybody in Earthquake community knows about it. Idea is that this is a waveform recorded by seismometer or our camera, but we don't have our camera, so this is a seismometer. You have a window of about 10 seconds, window of 1 second, and you compute energy, you make a ratio, you threshold, and you're done, and you know there's something going on at a particular moment. Simplistic, we implemented this, trivial to implement. So with this, we applied to our stations, and here, for every delta t step of 0.2 seconds, we represented every station as different color, and they kind of periodically repeat, and you can see kind of bands as they're triggered as more and more and more and more triggered going from down, going up. So this kind of reason, the kind of bands. Okay, we are happy. It's not perfect, it's not ideal, but this is something that is reasonable to us. Now, what we want to do, we want to predict time of arrival at some point. And what we are doing, we are going to basically treat in those bands, in these delta t time increments, we are going to try to estimate local velocity and find from this local velocity when the shock wave will arrive at a particular point. So our simplistic algorithm is that we, in this kind of band of particular delta t, we identify which stations triggered. For each triggered station, we find k stations nearest physically in distance from the past, earlier triggered. We compute, knowing the locations, we compute the speed of these, let's say, k stations. We use k = 3. And then we take a median. So we take a center one so that we throw out the outlying ones. And this is our local speed at every triggered station at particular increment of time delta t. So then what we do, we select 4 interest stations where we want to check the arrival time. And what we do, we predict arrival time based on this local speed. Oh, by the way, important thing I didn't mention is, because we expect errors, if there's a velocity that's outrageous, and we do get outrageous velocities, we throw out those stations and we only allow 3 to 9 kilometers range, that this is kind of something more reasonable. And we predict the time of arrival using median speed, but we do one more thing. Among all the stations that triggered in particular delta t, and we use them to compute arrival time, we use the lowest arrival time, the lowest number, the smallest. And that's our arrival time for every delta t. And we'll have plots for 4 different interest stations. And I'll show you some plots right now. So, and we are showing arrival time error, which is the predicted arrival time minus true arrival time, because we know it is given in the data. So if it arrives, if our prediction is lower than true arrival time, it will be negative. If it's later, it will be positive. So here is the first plot. We're using all the stations, all 1,800 stations. And this is at 4 of our interest points. And we see that we are predicting slight negative, but kind of reasonable. At the beginning, there's a big error because we're just starting. There's really not much information yet. So, and you can see these are all stations in gray. However, in color are those that were used to calculate particular velocities. They were deemed useful, and this is the predicted. For each station, there's a point on this graph. This is one single run, and we just didn't do like averaging a lot of runs. This is very preliminary. So now what we're asking questions is the following. We're using all 1,800 stations. How about if we use a fraction of those stations only? So we randomly downsampled to 25%. We're using only 400 stations. And then we do the same process, and our error kind of trickles up. It's kind of bigger range. You can see it's kind of smaller. It starts going up error. And then we go to only 10% of stations. And then errors start going up because we randomly selected only stations that we potentially could use. So, okay, makes sense. You have fewer recordings, fewer data. You're not going to do as well. More data, better. We usually know that, right? So this is basically all to do only with, we were learning. Until now, we learn how do we do something reasonable, not good, reasonable. Now, what we want to do next is, well, we know the cameras vibrate, and we want to somehow inject errors into our system. So what we do, we choose either 10% or 20% randomly stations out of all 1,800 stations, either about 180 or about 360 stations, and we completely change their triggers. So if a station selected is not triggered at all by the algorithm, STA-LTA, we'll trigger it randomly at random time within the span of whatever we are using. So randomly say, oh, it happened because a truck rolled by, because somebody used jackhammer. And then if a station already triggered, we will change the trigger time to random locations in the span, completely randomly, uniformly distributed. So we're injecting 10% to 20% errors, totally wrong. And then we want to see what will happen. So we have all stations, but 10 to 20% erroneous, as opposed to previous case, only 10 or 25%, but no errors. So here's the result with all stations. I'm reminding you the result we had with all stations, no errors. And now we are injecting 10% errors. So at the beginning, it's pretty big, but then it's kind of reasonable error. It's worse, of course, than here, much worse, but it's not super bad. And this is with 20%. So the errors, of course, cause issues, and we will have increased arrival time errors. But what we are arguing is that surveillance cameras can serve as not very reliable sensors for vibrations. And if we have a dense network of cameras, dense network of sensors, a lot of them, even though there are errors, we can estimate arrival time kind of similarly as if we had many fewer sensors, although they are reliable. So a lot of data with some errors, as opposed to much less data without errors. And because cameras are so prevalent, if we could leverage all these cameras, we don't have to install new sensors, boreholes, communicate. They communicate already. They are installed. Their locations are known. GPS coordinates typically are known. So all this is known. Now, the problem is you need to modify those cameras. They are not like, because you could theoretically take video and transmit to central location. That's why I was asking Tim about the centralized location. If you transmit to centralized location, it costs you bandwidth and time. But if you modify the firmware on the camera that can very quickly within its hardware detect that something is going on, even if it's erroneous, but detect it, you can instantaneously transmit it because cameras already are supported on transmission for video for surveillance. And FFT can be implemented on existing hardware of modern cameras. I'm not talking, analog old cameras. You need fast networking, but fast networking is needed in any EW because even though you detect, you have to warn. So it must be very reliable wireless or wired transmission that is not subject to delays. And finally, the most tricky point is local governments must take lead because there's regulatory issues. And there's also maintenance, some cost in maintenance and updating firmware and so on. So it's very speculative. It's something that is kind of pipe dream, but we have so many cameras and we have every day more and more cameras. Can they be used for good, not only just for surveillance? And this is very preliminary work. We are planning to do a little bit more, but thank you for your attention. And
so I was curious because this sort of crowdsourced earthquake early warning, it makes me think of the MyShake project. I don't know if you're familiar with that. I guess I'm curious if you've talked to those folks or what sort of lessons they learned translate and maybe which ones don't quite translate to the.
We actually had a few years ago, one of the authors of MyShake here at BU, he was giving a talk. So it's different because MyShake is using using accelerometer as the phones. So people have to install an app. Issues were with draining battery. So people are installing this, and it's a great idea. I think it's very similar to this. The difference is that in that case, it's individual user who opts in. This is more at the level, I wouldn't expect this to be individual person at home having a camera through the window. It would be like police, networks. University has cameras. Local government, Boston has a bunch of cameras installed everywhere, right? And also you have to be a bit careful because if you have a camera installed, for example, on a traffic light, these cameras are subject to wind load and vibrations are different because the frequency range is different. So it could be handled, but they typically will wobble. Whereas cameras installed on buildings are more static and they have fixed mounts, so they are more interesting. So there's different issues, but the same idea. Here it would have to be involved the government somehow, local governments.
And like on the algorithmic side, there'd be a lot of potentially commonalities as well, like in terms of like aggregating all the different signals.
Aggregating, yes. Detecting, no, because accelerometer versus camera. So detection different. Aggregation, I agree. I think the key point is that what I was asking Tim was, I would prefer this to be done in a distributed fashion rather than centralized, because then you have to send everything to one location, make a decision and warn. Whereas if the cameras can somehow talk to each other because they have local actually CPUs, but that's another issue of security, right? Because you need to transmit data between nodes and must be secure. And today we all worry about security, safety, and so on. So there are issues. I'm not saying I know what to do, but distributed would be really something that would be more interesting.
First of all, I should say that it was very interesting. The interesting part for me was that you are taking advantage of basically an amplification effect that the camera's mounting system has. And usually that helps you to detect a smaller earthquake, like those 4.4-ish earthquake that we consider as a very small earthquake. But then I have 3 questions.
Sure.
First is that, have you thought about instead of these interesting Fourier transform and shifting calculation, what if you just put a mark in the first frame and then use this AI-based tracking and then get the shaking? Have you thought about what we tried?
So how would you would need to have a feature point in the scene, not on the sensor, because the sensor will move, so it won't be helpful. It is the scene. Camera moves with respect to the scene. You want to have a fiduciary point in the scene to detect camera shape, right? So how do I put fiduciary point in the scene?
Like kind of in post-processing and stuff. I think that should be right to just track a point on the scene at artificial.
But this will require identifying a feature point, right? And in a way, what Fourier transform does, it looks globally at everything, and it says, how am I moving? What is it, happening, right? So I think this is good method, especially that it uses this magical FFT, which is extremely fast and supported on hardware.
That would be a whole pixel versus sequence.
Correct.
And then the second question is that for the alerting mechanism, we are trying something very difficult.
I'm sorry.
For the alerting mechanism and detection, that what you are trying to do basically is to measure the wave field in real time and also predict the future, which is something extremely complicated and ambitious even for seismologists.
That's why we didn't even read papers, because I didn't want to get bogged down in something that is extremely complicated. We wanted something logical and simple. And in fact, Prakash, who is sitting behind smiling, he has an idea that actually is along these lines, rather than estimating local velocities, estimate the wavefront. But this is more complicated.
Most of this can be complicated, especially like real-time, real early warning operational system, and that's why in early warning community we go with one actually alerting mechanism that I can tell.
I'm happy to learn more about this.
Thing, and that's how things work. Actually, all those early warning systems that you mentioned, they work on based on much simpler, basically alerting mechanism. And the last question was that have you thought about working with like the strong motion network? What it was? This was a strong motion network. You were using like
Yeah, we got data. We asked for like, can we get some reasonable data we can understand and not spend half a year on
The reason we went with the open over one in the first place was because you wanted dense data.
Right.
Yes.
So it was like, where could we find seismic data of the sort of dense, and there's not many.
That makes sense, but if you wanna do a more realistic kind of experiment, I think it makes sense to go with the strong motion network, which are accelerometer in the building. Which a lot of them are like government companies, and they have cameras. Yes. So then you would have a chance to make compare your like generated constructed waveform with the actual recording of acceleration on the same location from the same earthquake.
I didn't know that this data existed, so I'm happy to talk.
Well, I mean, there's also, instrumentation. I don't know how to get it, but I think the MIT building still has, the building at MIT still instrumental on every floor. Yeah. It's just the lack of earthquakes there. But I mean, it was there for the.
We were happy to get any data dense enough that we can test the hypothesis more noisy versus less more reliable.
First is to go from the complicated wave field like approximation to a simplified version that can be applied to a sparse network, and then from there you don't have any problem to get like data.
I think you're trying to do the two things. So I think you're doing the, comparing dense bad to sparse good, and then there's the alternative side of it, which you haven't tried at all, but yes, it's very.
And we are doing everything by cheating, simulating errors into seismic data, where really we should have 50,000 cameras recording an earthquake, which we don't. Yeah.
Questions for you mentioned the camera has to be far enough from the objects to make it work. I'm wondering, so you're converting basically displacement image to something, and how does the distance between your main objects to the camera affect your transformation?
So yes, I know. So that's what Mostafa said, is that the arm, depending how camera is mounted, may amplify the vibrations or may not. If it's very short, rigid on the wall, or it's long like a gimbal almost, and it will vibrate crazily in every direction. In this case, the distance will inform how big is the displacement. So in pixels, the waveform will be dependent, like this one, will depend on the distance. We are not interested in quantifying the vibrations. We're interested in only knowing there's no vibrations or there is vibration, really binary decision. We want to know something started, something happened. Maybe a jackhammer or maybe an earthquake, we don't know. But something started vibrating camera. We don't care how, that could be that it's very little, we ignore it, there would be thresholding, but we really focused only on, I'm sorry, what did I do? Something bad happened. What? I don't understand. I want to show next one when this window of energy rises. We want to really see when the energy goes up, and this is indication of starting of an earthquake.
So I'm asking because you choose a threshold, right?
For LTS, LTA, but okay, so I need to call it again, explain. We did one experiment with cameras because we harvested maybe 20 or 30 videos from YouTube. And we can detect vibrations, and based on the energy window, we can detect something going on. Finished experiment, throw out cameras. Now, use seismic data to find arrival time, but we need to somehow simulate cameras in this aspect, that we would replace every sensor with a camera. How do? We inject errors. We say randomly, somebody started a jackhammer, my camera says it's an earthquake. Incorrect, but we're injecting this into the network. We are not using camera data
in the second part of experiments because we don't have camera. I don't know the answer. We can chat later on. I can.
Yes, very interesting. Few questions. The first one is, do you know if we can have a reliable time on camera?
Most of the cameras are so mishandled that they need to be synchronized to NTP, network time protocol. And if they are, then it's okay. But good point. Are they synchronized to milliseconds?
Yeah.
Good, excellent question. Excellent question.
Good.
Second is GPS, right? It's mounted on the camera somewhere, right? Typically, surveillance cameras do not have GPS as your phone does. But a local authority that installed camera, like BU knows exactly every corner where camera is. I talked to police, BU police, and they know exactly at which corner the camera is installed. So they know coordinates. Is it to precision of 1 foot? Maybe not. Maybe 10 feet. Good enough? I don't know. You guys tell me.
But actually, since you probably will need to go with good cameras, because
yes,
of
modern camera. I'm talking last maybe 5 to 10 years.
Yes, maybe they do have actually motion correction, and maybe you can actually recover the parameter that they use for motion correction directly. I don't know.
Okay, good question. I do not think surveillance cameras do it, but I didn't think about it. Because when you take your regular camera and you take a picture and you turn on stabilizer, it will actually detect and it will remove your handshake, right? I do not think surveillance cameras do it, but another excellent question. I would have to dig deeper. Yeah. There's lots of questions.
Yeah.
There's so many questions. But I find compelling idea is we have millions of cameras and they are just looking, and mostly these cameras are doing nothing. Many companies install cameras and just feed it to nowhere. It goes into a black hole, don't even record it. But the point is, can they use somehow? And this is the whole premise. Yeah.
Yeah, that was great. Thank you. This reminds me of something I saw a long time ago after it was an earthquake either in Kobe, but I don't know if Kobe was pre-YouTube. There was a video on YouTube where you could see in a convenience store, the cans jumped up and then they slid. So you got the P wave and then the S wave. And they took a network of those around the city and were able to locate the earthquake fairly well. So it's all manual, but it's a different problem than yours because, right, you're going to first deconvolve the movement of the camera and then pull out the movement of the cans. But I was just wondering if there's auxiliary information that you could use like that, like swaying of something in your scene after you move the sort of spike between the FFT frames. Eventually. I mean, I know this is
zeroth order approximation. We are talking third order approximation. So this would be heavily scene dependent. Because normally what actually you pointed out, how far away, I didn't mention one thing which occurred to me while thinking about your question. Camera looking at this wall here is useless. There's no features. But typically nobody installs camera looking at the white wall, right? Unless something happens, somebody hit and it turned. Typically cameras look at the outside world. And buildings have a lot of features, windows and so on. And this is very useful for the Fourier transform to capture the translations. For your example, yes, there could be extra information, but it's not what we assume. In our case, ideal scenario is flat area, a lot of texture, and you can perfectly estimate. Buildings with different depth, structure in 3D makes a problem for this because the so-called optical flow is not constant, it's going to be spatially varying, and that causes issues for this method. But this is a different topic.
But the way like INSAR is processed, it uses all the features offsets.
I think it's an interesting question. I haven't thought about this. I'm trying to struggle with this very basic question.
Okay. Well, I think it's great to have a discussion, but there's lunch out there. So I think we should probably
thank you very much. I'll stop sharing.
And then we should try and get back to So hello, everyone. Thank you for inviting me. It's actually very interesting for me to be here today. And I could just take a train, which is not something I've been used to in the US, but in Europe, you do that all the time. So I was very pleased to do that. I'm actually someone that is exactly in the middle of the two communities that are here today, which is uncommon because usually either I talk to people which are just in the geoscience or in computer science, say, but it's pretty rare to have a bit of both. I did a bit of medical imaging, but then I moved during the last 5 years. I was already at ISTER, and I started to actually try to see how can we implement machine learning methods to actually deal with problems in geoscience, and more particularly in natural hazards and solid earth natural hazards. So I have worked with many colleagues, mostly in earthquake-related problems, but also in like volcano or landslides, etc. I will just focus on things that are related to earthquakes today. I did work with different types of data. So I did work with seismic data, also with GPS, but I'm not going to talk about them now just because I'm talking about recent works, because it's more fun to talk about recent works than old works. And also because it's a bit different from what I guessed people would talk here about. And I'm sure that Mostafa will talk about very interesting things in seismic data. So it's better to take a step aside to try to see what can we do on other things. I'm going to do that very fast, just to align on the terms that we're going to use, especially for the ones that are not in machine learning. Just remember, because that's going to be useful for the talk, that when we talk about machine learning, it's actually, we talk about three things. First, we talk about collecting data, and this is 90% of the job. Collect data. Collect data, meaning collecting data where we have inputs. So, okay, if I want to predict an earthquake, then I can have different information from my inputs. If I want to predict size the electrical consumption of a house, I need information such as the superficie of the house, etc., etc. And then I need my output for every house. I need to know, okay, what is the electrical consumption so that I can build a model based on that. So I need both inputs and outputs. So of course, an input can be a signal, an image, such as the output, but I need to have what I call features, okay, but also what I call target or labels. This is for supervised learning, right? And then I just learn my model, which here would be the green line, not a physical model, it's just a machine learning model, but it's the same thing. And then we predict to apply to test sample, to new samples, what is the output. Okay, so the main thing is, can we actually define problems where we have both input and output on some data so that we can learn to use it for new data? And I'm gonna try to summarize in a weird way the types of problems that have been tackled in geoscience, let's say. The first type is the type where the problems where we can have access to large sets of data with the labels. Okay, so with the targets, and these are the problems that are the first tackled. Okay, because it means that we can have access to a large set of data where we have labels by other means. Okay, so the easiest example is this peaking and all of what comes next from seismograms, where we have input is the seismogram, and the output of the label is actually the time, the onset time of the PNS wave. Okay, and why was it very easy to use machine learning? Because manual people and semi-automatic methods did label a lot of seismograms. So now it was easy to build a model. Okay, so this is the first type of problem that has been tackled, and there's a lot of examples. The second type is unsupervised problem. Okay, so it's a problem where we don't know what we're looking for. So if we are thinking about my small schema, it means I don't have any output. I don't have a label, but I just have my data, which can be just features, but it can be more complex, can be images and so on. And I try to understand, okay? I try to explore, okay? So for example, I can do, reduction, dimensionality reduction, I think clustering, etc. One of the examples that has been done recently, talking to you guys, is really trying to see, okay, can we extract some information from a continuous seismogram? Okay, so involving dimensionality reduction, transforms, thanks to wavelet transforms, etc., trying to then find a meaningful representation of the continuous signals so that we can cluster in time and try to identify maybe new signals. So we know there's earthquakes, we know that there's noise, but actually in this noise, there might be more things than that. So we want to explore, okay? So we will cluster the times and try to see if there's times actually that do relate to something else. For example, to change in weather, so that actually there's signals that we can learn from that. Okay, so this is really exploration. And then there's kind of a third type. We'll see that there's actually more after that, where it's problems where we don't have access to a large set of data with samples that are labeled, but we can try to simulate data and try to simulate very realistic data. This is hard because it means that you need to really simulate data that are realistic. Why? Because if you remember my slide here, I can predict something only if I am inside inside what I've learned. What I've learned, so inside basically my original data. Okay. If I am outside, if I have a point here, okay, my input is there, maybe my model will not work. Okay. So I need to be inside the space of what I trained on. So it means that if I simulate, I need to actually simulate something that is very close to the real thing so that I can actually use it for real cases. Otherwise, it's less useful. So I'm going to show you two examples of projects, ongoing projects that deal with that. And why do I work on that kind of project? Because I'm someone really in between. I am in an earth science lab, so I have access to people that exactly know what they're doing. And they have questions that they want to solve. And so we can solve them together because we are just, living together. So the first problem is actually more linked to geomorphology. Okay, so we want to characterize active faults. Okay, so what is an active fault? So this would be something active, but it's actually very old. Okay, so it's something that has made an earthquake thousands of years ago, but then now has undergone erosion, a lot of things. So there was a movement like that, but then a lot of things happened in the landscape. Okay, and what Leah, my colleague, wanted to know is that, okay, I need to extract the step. Okay, the size of the step here, you can see it here, because it measures the strength of the earthquake at that time. And so since this active can actually reproduce, it's very important for a large number of reasons. So I said, well, that's relatively easy. Why do you even ask me? You can just calculate it, right? Because you just take a ruler and you calculate it, so you can automatize that. She said, well, yeah, there are some semi-automatic methods, but they don't really work because the reality is way more complex. There's erosion, there's things that move, there's different walls, there's a lot of things going on, trees, etc. So actually, when we take a profile like that, it does not really necessarily look as smooth as that or as sharp as that, but way more complex. And so the automatic methods, they fail most of the time. The semi-automatic methods. And the manual methods were they're not very reliable. And second, they're very time consuming. So she really wanted to process a lot of data. So said, okay, well, we can do that. So in that case, what we have as input, we would have our profile, okay, so 1D profile. And as output, we would have, okay, the size of the scarp, which here is relatively easy to compute, okay. And I said, well, it's not a time series, but what you're giving to me is actually a 1D signal. Okay, it's just a spatial signal.
Tim is in the waiting room.
I can't do that, right? Yeah. Okay. So this would be a 1D signal just in distance and not in time. Okay, it's the altitude across time, because here we're looking at a digital elevation model. Okay, so we have altitude. And altitude and distance, sorry, and not time. And what we want is just the height. Actually, what she wanted also is something that would also give us an information about the uncertainty, because there is a notion of uncertainty. So we actually came up with a model, with a Bayesian model. But that's a bit on the side. And okay, so this is relatively easy. The goal is not to make something very complex because problem is not that complex. Okay, the difficulty here is that we don't have a lot of existing profiles where we know the scar, because earthquakes have happened a long time ago. So then, well, we don't know exactly what was the scar. Okay, so I said, well, if you don't have a lot of profiles and a lot of varieties of profiles, we will not be able to train a model in that. And then I said, well, maybe you can simulate them. And then she said, of course, yeah, because, you know, she's a geologist, so she knows a lot of things, and she knows what to simulate so that it's realistic. So she simulated a variety, 5,000 faults with a large number of variations in terms of wall, in terms of secondary faults that could be on the sides, of course, of the faults that we are measuring, where we would want to actually know the height and when we keep it, because this would be our label for later. But we also add perturbations that are realistic. So it's just noise, but also noise that are a bit bigger so that it simulates maybe holes or maybe trees, etc. And then we learn our convolutional neural network that is not so complicated. But the main problem was to actually fit a data set that can actually be used after on real cases. The large problem here is to always be close to the real cases so that you don't solve a problem that is useful for nobody. So then we tried on different examples. So here is a fault here that I think it's in Malawi. And then you can do some cuts along the faults. So these are examples of profiles that you can have. You can see a variety of profiles. And then what we did is to actually compare, because the problem is that there is no ground truth. We cannot really be sure about something on the real cases. On the simulated cases, we can, but what we are really interested in the real case. But what we can do is that we can compare with manual annotations from experts and also semi-automatic. So we could see that, okay, we can validate. And the more important thing is that we can scan now very quickly, efficiently, all of faults, especially not just restricting ourselves to few profiles, but actually scan a large number of people. And then we had a visitor, because so Leah presented this work, and then the students say, oh, that's very nice. I want to use it on my faults, but my faults are underwater. So I said, oh, sure, but then is your data similar to ours? And then she said, well, yes and no, because what the problem she had is that basically underwater, you have a lot more erosions. You don't have trees, but you have holes, which are pockmarks. Okay, so we actually simulated a new data set that works specifically for bathymetry. And this has also proven to be very efficient. Okay, and so what's next? Well, for now on this project, we are looking at strike-slip faults, because for now it was just normal faults. Problem with strike-slip faults is that you cannot take just a profile. You need to look at the full 2D view. And what geomorphologists do, that they see these kind of landscapes, and then they try to, move the small pieces of papers to try to align them. What do they align? They align, for example, rivers, which are markers. They try to align them together. Okay, so can we do something with that? So I was more skeptical, but I think we'll make it work. Why? Because since we're in 2D, we need to simulate things a bit harder now. So this is exactly, so here would be like a large fault, here it's small, etc. So you want to quantify these displacements. So there's a lot of complexity in the river, in the markers. And so, okay, first we have to come up with to formulate well the problem. So here, okay, the very basic problem that we can think of is, okay, we have an image where we would have, for example, the fault in the middle, a marker that goes on the fault, and the output of this model would be the offset. So the image here would be, again, this digital elevation model. So basically the altitude. Okay, we just have a map of the altitude, and we can try to extract the offset here. Again, we don't have a lot of data. We have a few hundreds of data, and they're very, very correlated together. So if you do use that, then we cannot solve anything. So can we try to generate a realistic database? So what we did, again, here is that you want to try to generate a database that is as close as possible to the real case. So if you don't need to generate database, just don't. It's always simple. So here, what we do is we try to get as much possible as real things. So we actually take digital elevation models from existing regions where there is a river. For example, here, blue would be down and green goes higher and higher. And we take some rivers that we extracted automatically that goes there. And then we are using what we call dynamical model that simulates erosion, but we also included some faults, so we can actually include a fault, and then here it's actually a fault that is pretty recent, then use it to actually continuing the erosion so that it looks more realistic. So we can learn from that. Again, this would be our input, and the output is the fault that we will add to that. So it's controlled so that it allows us to know the label and to build a model where we have the full supervision. It's working on synthetics, but that's not really interesting. It's always working on synthetics because that's what you train. Okay, what really matters is that it works on real cases. So it does work on some of them, but we're still getting there to really make it work on real cases. So it's just to show you that it's a back and forth between data and model. Okay, so there's a continuous back and forth. We have a lot of ideas about how to improve the model, how to include a few data samples that we have, the real one, but we're not there yet. We need to first be sure that the database we have is enough good to actually have a first prototype so that we can build. Okay, I'm going to move to the next example, which is a bit different and maybe a bit closer to what you guys are working on, because it looks at recent ruptures. Okay, so I'm talking here about optical image correlation. So when the rupture just arrived, you can actually perform a displacement map, okay, which is a map that shows you all of what has moved between two images. Okay, so concretely, that you have two images. So here I'm talking about optical correlation. So it's actually performing the difference between two optical images, okay, so before and after the earthquake, to try to see where did every pixel go. Okay, so you have like that a map of all the displacements. Okay, so for example, here I think this was in Balochistan. You can see that there was an earthquake here, and you can see that those pixels moved a lot. Okay, this is actually in the east-west direction, and this is in the north-south. So you actually get a displacement field. Okay. And the complexity of the task is that it's subpixel. So it's usually you want to estimate a displacement that is of the order of the pixel, sometimes a bit few pixels, sometimes lower than the pixel. So typically up to 0.1 pixel. So it's possible because you assume that you have something relatively smooth, at least except on the fault. But it makes everything complicated, especially because between the two images, there's few weeks, few months, things have moved. So it gives, everything is a bit more complicated than what it is. Just to know that these kind of maps can also be done with INSAR, with low interference radar, but it's very, very different kind of application. Okay, so this exists, and it actually relates to one talk we saw earlier, because typically the methods that perform that, they use correlation. So that's why we use distant correlation. It's not really a machine learning term, because correlation is for something else in machine learning, but they use it for this problem because what they do is that they correlate the two locally, some small patches of the two images to try to actually estimate the best fit. So they try to maximize the correlation either in space or actually in the Fourier domain also to do that. But then it's always local. Okay, so it's very local, and if there is noise, then they don't resolve it. And then, for example, here you can see the stripes, but there's also roads, there's a lot of things. On the fold, they have problems because they try to actually estimate the best fit, but it's a smooth fit on a small patch, and if you cross a boundary, it doesn't work anymore, etc., etc. Remember that this is subpixel, so actually it's a bit different from what we saw earlier. in your talk because they do that sub-pixel. So it's actually, they try to estimate the best correlation, but lower than a pixel. So it's very time consuming also because of it. Okay, so if we look around us, what does exist in machine learning and what does exist in the rest of the world to deal with this kind of problems? You can think about an analog problem, which is optical flow estimation. So typically for car, you want to estimate the movement of the objects behind you, okay, surrounding you. So for example, you want to estimate the cars. Okay. So it's very similar in the way that what we are interested in, what they calculate here is the flow, so the difference between the two images. So here would be a flow in 3D, maybe not in 2D, but it's very similar in terms of problems. And now state-of-the-art models for that are machine learning models and deep learning models. So we can think, well, maybe it can solve also, it can improve and go faster for our task goals. So there it goes from very simple models such as convolutional based models, which are here type unit. And now there's even more complex. So this is like one of the state of the art, which is Konrad. And this does work well. And what do they do to train on for that? Well, they usually have data sets such as this one, which is called flying chairs. So it's chairs flying in the air. So they have different frames like that. And they move the objects, and they have a fake background, okay? So they completely control what they move, and then they can actually have a data set that is fully controlled. This is the movement of the chairs, of the different objects that they move differently, and they know the background is fixed, etc. So it's fairly similar to our problem, but we cannot use their model directly on our problem. Why? Well, because they focus on dynamic, dense motions of few objects, which is exactly not what we are interested in because our whole land moves, but very subtle. They don't usually have a lot of noise because they suppose that the two images are separated by seconds, okay, or milliseconds for video. Okay. And they don't care about subpixel accuracy. They just are interested in the big movements. Okay. So we have a bit different problems for that. So, okay, what do? Well, the problem again is that we don't have a database, a real database. We have a lot of images, but they're not labeled. We don't know the displacements between them. Okay, at least we don't know the good displacement. We just have an estimate of the displacement that was performed by other people. So what we did is that we performed a database, okay, an ultra-realistic. Why do we mean ultra-realistic? Because what we started on is based on real satellite images. I would not simulate satellite images for no reason. We can take real images on regions where there's nothing that moves, okay? No earthquakes. Okay, so we take pairs of images on regions that are relatively stable, okay, but acquired at different dates. And then on the other side, what we can do is to simulate an earthquake, so displacement field. Okay, so in order to have a fault that is relatively realistic, we actually simulate a fault in 3D, and then we estimate a displacement field that is relatively realistic, and we generate a lot of them. And it just leaves us the last part, which is resampling. So it's basically we warp the second image, which is supposed to not have moved, with that. So the good thing is that we do have natural changes between the two images, and then we include a displacement that we fully control. So now with our database that is relatively large, we can train a model from that. So the database is actually available. So here, the first test that we did is with a model that is just a UNet. So it's actually two versions of UNets that perform similar quality. And then we actually have some patches. So you can input some patches into the model, and it gives you the full result of the full patch. So then after that, we just need to actually perform a sliding window, but a sliding window of 1,000 patches, which means it goes way faster than what was done previously on patches of like 10 pixel by 10 pixels. So this is the first model that we performed, and it works on real data. So this is, I think it's request. So we have our two models and we compare with the existing methods because it's still very important. They do perform relatively well. So which are, this one is spectral based and this one is spatial based correlation methods. And we do see that we have smoother results and the fault is relatively sharp, which is supposed to be. And it does not have these weird patterns that are not realistic on other, such as on other methods. Still not perfect. Oh yeah, so one thing we also did with another colleague is to try to apply this kind of same methods, but for synthetic aperture radar amplitude images, which are other type of images that are a bit weird because it's basically just azimuth and range, and there is it's a weird vision of the Earth. So we actually perform this whole operation on this weird vision of the Earth before transforming to the geometrical natural representation, and it does also work relatively well. Okay, so this is the example on the SAR data. Okay, but so now that we have our database, which is the core of future works, can we actually do better in terms of deep learning? Can we actually improve the model now that we do have our input and output database so that it works specifically well for our task? So this is a collaboration with people at Grenoble on computer vision lab. And so what we saw is that our original model, so GeoFlowNet, it still has room for improvement. So for example, here we have pairs of images and the GeoFlowNet is here. And trust me, because you're far, the other methods could well define some secondary faults. Whereas in the case of the GeoFlowNet, it was very smooth. And so actually it was not very well defined. So clearly there's room for improvement there. The problem is that if you just use optical flow models, even though you retrain them, just such as the RAFT model, it doesn't work at all. So this is the RAFT model that is one of the state-of-the-art in optical flow. It doesn't work at all. So we actually investigated why, and we actually investigated a model that is able to perform good on our task, which is able to have something relatively smooth, to see the faults, to also, when there is some weird artifacts, for example, here there is a basin and so on, is able to smooth out relatively well the parts that should. And how did we do that? Well, we perform something which is like with refinement. So we actually warp in the middle and then we train end-to-end so that there are actually steps with refinements. We perform something that is not done in the optical flow community, which is this correlation independent backbone, because otherwise for the subpixel part, it was not working for us. And we also had something which is specific, which is a regularization layer, because we have a specificity that we do include some noise between the images. So at the end, there will still be some parts that are not. Okay, so I'm mostly done. So what's next? Usually here I talk about the fact that we want to predict earthquakes, and I show how it's not that easy and that we should not trust all of the papers out there to predict earthquakes, because machine learning can do a lot of things if you just overfit. But I thought that that was covered by other people, and it was, so I'm not going to talk about that. Actually, there is a first problem, I think, today that can be solved. It's a problem where we don't have a large set of data, but we have a limited amount of labeled data. Okay. Yet we think that we can take benefit of foundation models. So this is really related to what we've seen before. Okay, so I'm going to show with an example. So on my side, I have problems where, for example, now I don't want to characterize, I don't want to estimate a scarp, but I want to detect. I want to detect all the full scarps, so the all full scarps that are barely visible in the landscape. And for that, I can use DEM, so digital elevation models. I can also use optical images, but that's all I have. And what I want is to have like those faults that are barely visible and to detect them, okay? To detect that. So I can use the database, manual database that was made by experts. For example, this is in Peru. I can do the same also for INSAR problems. So here, again, I also want to detect things, but I want to detect fault or landslide, but this is rapid movements, existing movements, because we are looking between two instants. And this is, for example, a landslide. We want to do that with other Earth movements. And we can manually delineate things that we check are movements. Okay, but even though it's going to be hundreds or thousands, it's still going to be small compared to the difficulty of the task. Okay? So this is manual database. But I think that what we can do is actually take benefit of this self-supervised learning, where we would actually learn from a task that is easy to collect a lot of data. So this is what is self-supervised. For example, here I would mask part of my image, reconstruct it, and then use this encoding on downstream tasks that are, for example, this full scarp segmentation, but I hope maybe more than just my 2 tasks now. Maybe it can be used for something else. I can do the same also for specifically for a task of detecting movements on INSAR, maybe actually taking the benefit of other data. So this goes into the big, large foundation models that we've seen. So it's not just about training for one task, but training as a whole, and then use it on different tasks. So again, this is embedded in more large problems. So we have seen a lot about how to maybe build models for seismographs. Okay, so these kind of models that can be used differently. There is a lot of things going on also in the remote sensing community. Problem is that they don't care about our problems. They don't care about DEMs because they don't care about the geomorphology. They don't care about INSAR. So we cannot resolve for our tasks. So that's why we need to do. We can still take benefit of the environment that exists. And when we talk about that, then of course, okay, maybe this is the way that we can actually handle multimodality. Okay? So multimodality can be, okay, different sensors, for example, different remote sensing, or maybe different seismic data. But can we actually take benefit from the different types of data? So can we, this is already very old in the machine learning community, but can we actually find a way now to, use maybe remote sensing together with seismic data or with something else at the same time in our input model? I think it's not been really investigated because we have to find the right problem for that also. And then the right data set, because we are dealing with things that are way harder than what are showing here, where the audio is directly related to the video and with a kind of similar frequency, etc. But I think we're going to go there. Then there's the whole thing about, can we actually use labeled laboratory experiments and not what I've simulated with my computer? So this was Chris Marron a few weeks ago, where he showed that, well, yeah, we can try to use earthquakes and can learn from that, but he's actually using it to understand, not to use it on some new earthquakes on the real cases, more to understand things about the physics of the earthquakes. Okay, so which is, I think, very, very clever and very interesting. But I think it's still hard. So I know Jan Klinger is trying to set up projects that from analog then apply to real cases. So to learn from analog models and apply to real cases. I think we're still far from there. I wish him good luck, but it would be interesting, I think, to see if we can make it. So a lot of work in the next year. Yes.
So you used a lot of words that I'm very familiar with because I worked all my life in optical flow and all this stuff. So I'm trying to understand what you're trying to detect. So you have, let's say, a satellite flying over area.
Yes.
And then
I'm trying to detect anything. Yeah.
No, but you're trying to find deformation due to the slip.
Yes, basically there's an earthquake that happens. You have an image before and an image after.
Right.
And you're trying to see how every piece of the earth moves.
Right. But can you think of this as a rigid body transformation? Because satellite is very high above the ground.
Yeah.
Are you assuming that there's a local deformation on the surface of the Earth, or this is just a slip, which is just a translation?
It's not just a slip. It's more complex than that. There is on-fold and off-fold deformation. So the pattern is actually not just basically two different rigid bodies that move one and
so this is why you need optical flow, and affine wouldn't do, even though it's high and it's very flat, right?
Exactly. So if I have one example, yeah, you can see that it's here. For example, there is a pattern which is here. There is a lot of deformation and it goes smooth or after, but it's not always the case. It depends on the earthquake. So you don't have a full like two rigid bodies. Yeah.
Because then it would be just affine with two different sets of parameters.
Yeah, it's not that.
Work.
And actually, that's what people are interested in. So the earthquake experts, they're interested in actually how much energy is released on the rupture and how much is actually accommodated and how far. So you cannot take too much assumptions on that, because otherwise they actually are not going to use your tool.
So you mentioned FlowNet and the other method.
Yeah.
Deep learning is excellent. There's two areas where still it cannot outperform significantly or at all video. One is optical flow, which is approaching very closely, but model-based methods are still about roughly the same. And second area is video compression. No matter what is done so far, it's about the same. It cannot be better.
Yeah.
So have you tried any model-based methods like classical based on regularization, TTs?
Yeah, we do, because we do have already existing methods.
I see, based on optical flow.
So, which are not optical flow. So we do use them. And what we actually tried, which we might come back, is actually to combine the two, because we still think that the correlation-based approach is not bad. Is actually, if the data is perfect, it's the best we can have. But the data is not perfect, and that's the whole thing. But can we actually combine? So we actually try to find models that, so I did not talk about that at the end, but actually how to use a bit of, so it's like physical-based models. Which in the end did not work that well, because I think, I mean, it's complicated, but it's still a way to go to actually combine the two. I agree.
Thank you.
I have a more, I don't know how to describe it. So a lot of times when we try to use synthetic data to train the model, and sometimes when we apply to real data, it just didn't work.
Yes.
And sometimes it sort of work. But so I'm wondering, for example, in the geomorphology case, or maybe others, have you been to a situation where you decide, oh, the synthetics are not real enough?
Of course.
You have to do something about it.
Yeah, always.
What's your experience regarding that?
It's just that you have to first have a rough idea about whether your synthetics will have the ability to be enough or not, because if I would just manually simulate something, I mean it depends on the problem. Sometimes you feel like, okay, it's not going to be enough, so you don't even try. When you can try, you have to have your real data, some of them, close, and always monitor on that, because that's the point. It's to make it work on real data. So if you just work on the synthetics for too long, well, you're just solving something that nobody cares about. So you have to do back and forth, and we do, and we always do. In this case, we did. In the other, we did, because we are like, oh yeah, it doesn't work because of that. Oh, maybe it doesn't work because of that. Oh, we forgot that, and so it works only on some cases and not in others. So there is a back and forth. So that's why it's not just you have a data set and you have a model, but it's at the beginning it's a back and forth. Then once you have something that is a prototype that works relatively well, you have a database that can be used by a lot of people, by me or by other people, and improve the machine learning behind it. So that's, I think it's, the first base is not with too much massive machine learning, because anyways, the first step is really the data. And so you need a basic machine learning that should give an overall result, an overall result that is more or less good. And as long as you don't have that, you just continue working on that.
So the GeoFlow net is trained only using synthetic.
Yeah.
Is it possible to label some small amount of data, like real data, or is that not really?
Well, it depends what you want. You can use these kind of results, which are based on existing correlation methods. They're not perfect, so you will not get better than that. That's the problem. That it's not bad, but it's not. If you want to resolve their problems, it will not work, because. So on this case, actually, even few. So we have ideas about few real data, because on some cases you have several, on Ridgecrest, for example, several different acquisitions at different resolutions. So you can use the a high resolution to be basically your ground truth for the lower resolution. But that's all you can do. So it's very, very small.
Just say a little bit more about how you're thinking about using that in the audio text.
Well, so I don't know if it's just an example that I show, because the figure is it's not too complex and relatively easy to understand. It's just that now that behind these foundation models, it's transformers, and transformers take as an embedding that is basically, it's something that where you can actually combine different types of data more easily. It's basically just something that is a vector. And so thanks to that, it was possible. And actually the foundation models, some of the foundation models that exist for other things, they can input variety of data. So it's not always the case. And I don't know if we should put everything. That's not, but it's more easy to input different things together. The difficulty is that then you have something that is very high dimensional and complex. And so it's, everything is more complicated. So you have to first find, problems where that could be useful, but I think there is. And second, because of the self-supervised in the foundation model, you could train a model that used these different information together. Still, there's a lot of things to be done, again, because we're talking for us about things that are really not of the same order of for example, frequency. If we talk about remote sensing and seismic data, even seismic data and GPS, it's things that are, one is every millisecond, the other is every day. So it's hard to really, but theoretically, we should be able to do something instead of just, separating. But people already do a bit, but it's just that I think that's where people would go.
You can learn a system where you can observe many different modes of data, then apply it to a system where you can only observe one or two.
Can, yeah. The foundation models do work like that. It's okay if you don't have all of the modalities at once. This is
probably speaker. Thank you very much again. Our last speaker is Mostafa Mousavi from Harvard. Also Google. Go with Google. Yep, go with Google. Anyway, yeah.
There might have been someone in the Zoom.
Oh, yeah.
Zoom shared. There was. It's just that it looks like.
Oh, right. I see. Yes, they shared. Yes, it's true.
This is will be popping up, right?
Yeah.
Yeah. Okay.
Okay. Thank you. Thank you for having me again. It's good to be back here. What I'm going to present you today is a little bit different than most of the work that you have been seen like earlier this morning, in the sense that there is no training involved, there is no training data at all, and it's a very different type of machine learning seismology, and it's different from my own works in the sense that you won't see any seismic data in this study. Imagine this, that you are trying to recreate your grandma's legendary lasagna, one of those with like handwritten sausage stain recipe card that is missing some critical instruction. You just snap a photo of that faded recipe, pass it to an LLM with a font like this, and in a second, it's not only able to fill the blank with its vast knowledge of cooking techniques and also ingredient interaction, it also provides you a professional waiter level like wine recommendation. Not a long time ago, this, what I just described you, could be a scene from a futuristic movie, but today this is a like typical familiar example of like type of LLM application in our daily lives that perhaps most of you have tried something similar to what I just described. So LLMs are everywhere these days. They entangle into our daily life. They are used to translate languages, to summarize text, to help us writing codes or emails, etc. So now imagine that if they could revolutionize our daily life and also or the way that we interact with technology, what they can do if for difficult challenges in our scientific fields. So today, basically, I'm going to show you that what else they can do beyond just translating or helping you writing a text. I will mainly talk about one application, which is to estimate the intensity of earthquake ground shaking using unconventional data. And at the end, I will just show you a few examples of other seismological tasks that they are able to perform. Earthquake magnitude is basically a measure of the size of earthquake at its source. So earthquakes of similar size, similar magnitude, they can have very different ground shaking on the surface. So this is why the ground shaking intensity measures are used to basically reflect the strength of ground shaking at the surface at particular location during an earthquake, reflecting the earthquake impact on people, structure, and environment. They have a lot of application in seismology. Pre-earthquake period, they are used in seismic hazard mapping, risk assessment. During the earthquake, they are used in earthquake early warning system, and also in post-earthquake scenarios, they are used for damage assessment. These rapid shake maps that are used a lot in like recovery planning and loss estimation. In past, they have been the way that to estimate the intensity was through like expert surveys, going to site location by location. But in recent years, in current time, the way to collect this data in at a scale is through online questionnaires like did you fill it survey by USGS or interactive illustration like this used by other agencies like EMS. But both of these are like kind of active participation. They require active participation of user. They need to go to this website after they felt an earthquake and fill out this relatively long survey. So here the central goal was very simple to see that if LLMs can use public, unconventional, unstructured data, like what eyewitnesses post on social media platform, and estimate the intensity of the ground shaking at that location. To test this, we collected data simply in forms of a screenshot or a screen recording on 3 platforms of X, TikTok, and YouTube. The data that we collected include some simple short posts like this one, or the one that includes some relevant information. We collected data in different languages. There are some videos where a person described their experience or what they observed during the earthquake, and then some surveillance camera footage showing the intensity of shaking. indoor behavior of animals, humans, or outdoor footages. We were only limited to use data that we can correlate with the ground truth earthquake and also have some location identifier in them that we can use to pinpoint the location where that posts were made. This reduced our data to around roughly 90 samples for around 7 earthquakes, ranging from 4.5, 4.6 to 9.1. Then we designed a simple prompt based on the information that are useful in estimating the ground shaking intensity. We designed a prompt that direct the attention of network toward the information that are useful to quantify the shaking, and also provide a few examples of input-output. So that's a few shot learning problem. Then implemented a simple pipeline like this in Google Cloud that automatically first of all, we are using Gemini 1.5, the earliest model that was what was available at the time. Automatically, it takes these videos and audios, and then first there is a simpler prompt that extracts the geolocation from the content of the post and use that to estimate the epicentral distance to the earthquake. This distance plus the magnitude of the earthquake are added to that generic prompt that I showed you earlier, and then pass it to the model and query for the intensity of ground shaking in MMI or modified Mercalli intensity scale. And the output would be estimate of intensity plus the available information, observation, evidences, reasoning, etc. This is an example of input-output. So on the left, that's a screenshot of a tweet where a resident of New York City mentioned that she felt an earthquake, and there are some relevant information like this to retweet confirming that they felt the same earthquake, and then we intentionally include some irrelevant information. The output of Gemini, just part of the output is listed here. It takes the location, time, the reaction of the human, surprise and curiosity based on this wow. At the end, replies have been used as a confirmation of the earthquake. And then it came to a relatively good estimate of intensity. It worked well actually in other languages, and it's really interesting to see how much of information you can find. In this case, that was a cooking blog actually, where the porter would ask about their experience during the earthquake, and they even not only they mentioned very well that how the earthquake they actually pointed toward a small foreshot before the Noto earthquake that was actually unknown at the beginning, and later seismologists figured it out. They mentioned also receiving of earthquake early warning. This is a more complex scene where there is a video, audio, and then there are some text in the caption. It was able to analyze this, extract all relevant information from all these multimodal domain, and then narrow down to a very good estimate of intensity. When it comes to evaluating these results, the problem that we have was to estimate the location, which is very necessary to validate the output. And it can be challenging in cases like this, where there is not that much of location identifier. But there are some cases like this one that is, we can have a very good idea that where this video has been recorded. The estimate, as you can see, is very close. Surprising is like kind of in decimal accuracy, close to the ground truth. And there are a lot of good examples that we've processed, but I think this one can be a good one to show you every things that they can do. It's a complex thing of many things going on, but you see that it extracts the location, approximate duration of the shaking, the reaction of that human, the driver that was present in the scene, but we never saw himself, the language of that navigation system, the music that was playing on the background, the ground movement, falling of the rock, car vibration, human voice, car navigation system, everything together, and it narrowed down to this estimate of MMI between 6 to 7 MMI. And then we have the reasoning that makes absolute sense, especially to X. And this example, the second example that I picked you, is just to show you the potential of this type of unconventional data and how much information can be extracted from this. Just play this one. Only a TikToker can convey that much of information with details in less than 30 seconds. A lot of, and then just to give you an idea how magnitude 9.1 gonna look like, this is some videos from Tohoku earthquake, which this camera recorded 2 minutes of shaking in that level of intensity. So information is there. It is very useful things that we can do with them. Here, the blue dots are estimates of Gemini for intensity of ground shaking at different locations for 2 earthquakes using those posts, combination of them. The light blue dots on the background, these are the intensities estimated from the felt report, those online questionnaires. And then we have intensities estimated from seismic sensor shown by a triangle, and the gray and red lines are the theoretical basically relationship. And as you can see, they are in a good enough agreement with considering the uncertainties that are common in MMI estimate. Here, each box part basically shows the distribution and outliers of the intensities at specific zip codes in cities based on the Geophysicist reports. The Gemini's estimates are shown by this circle. As you can see, they are a quite good agreement from low to high intensity level and from mid-size to larger earthquake. Another good thing is that they can process multiple posts at the same time and give you an estimate of ground shaking intensity based on the cumulative and collective information available in co-located posts. what I showed you was where including that magnitude and distance into the prompt. If you remove them, as you can see, the accuracy of output drops, which I will come back to this later. But before that, we try to estimate the uncertainty of model using bootstrapping, and then also by asking the model itself to rate its confidence on the output. The general pattern makes sense. There is less uncertainties with the information extracted from videos as opposed to the posts that include less information. But we found that model has a little bit of overestimation on its confidence. I didn't show you the detail of the prompt, but we never defined what is MMI or what is the intensity scale. The model, it already knows what it is and how to estimate it. And the good thing is that it can do that for different type of intensity scale, EMS, JMA, and it already knows all of them. It doesn't work perfectly all the time. These are some examples where the model identified the barking of this dot, which was the only thing that she was not doing. So we ran another inference and it get even worse by seeing two dots in this scene. So this type of hallucination exists, but we don't think it can be any prop. Why? First of all, they happen very infrequently. In our case, just 3 out of 90 samples include that type of problem. And the other thing is that we think that what the model sees and hear or read from the data is not the only thing that it uses to compute that estimate of intensity. This can explain that we picked a video recorded 5 kilometers from 7.5 earthquake in Japan. That's the ground truth, the location that it was recorded, and the ground truth intensity was 8. But then we ran multiple inference, and each time we intentionally changed the distance to the epicenter, keeping everything else same. As you can see, as we increase the distance, epicentral distance, the model adopted and adjusted its output and lowering and lower its estimated intensity, which is in a similar fashion that we expect from the attenuation relationship in earthquake seismology. But it plateaued between 3 to 4, just based on which is where attenuation relationship says that there should be no way that you feel an earthquake of this size with like 1,000 kilometers away. But the model, as it was seeing clear evidences of shaking in the video, it never reduced its estimate. So it's a combination of the knowledge and also some evidences and information that it collects from the data. Similar thing happened when we processed the tweet. Second example, we did the similar thing. This time we kept everything same, except the magnitude. We intentionally changed the magnitude, and as you can see, the responses of the model again change in a similar fashion to a ground motion prediction equation. So does this suggest that the model knows a GMP? We ask, and it turns out yes, they do know what is the relationship between magnitude, distance, and intensity of the earthquake. But then the question was that which GMP does it do a cheating by just learning an equation from the internet and then using it to come with this estimate? Again, we asked. what you heard is actually Gemini claiming that it has its own GMP, which is apparently different than what we have in seismology, but apparently it works. So how Gemini build it, based on what data, from where, which model, we don't know, but clearly we can see running large number of inferences that we can see there is an underlying relationship, that it picks randomly from internet, from what data, we don't know, but they know something specific about the earthquake seismology. To not make the talk like a Gemini advertisement, I put you this slide to show you that ChatGPT can do the same thing, but not with the decimal precision that the Gemini does, which may suggest that it doesn't have that like type of underlying like the GMP relationship. And this opens a whole like new era that what else is large language model know about the Earth and its physical processes. Here, we ran a large number of inferences asking Gemini about the velocity of P wave and S wave at different depths. And it turned out actually it knows kind of well the velocity structure at the crustal depths, but not deeper part of the Earth, which is not bad. Then we just plotted a 3D seismogram like this, and then provided to the model asking to pick P wave, S wave, estimate the distance to the source, magnitude, etc. As you can see, the prompt is very simple. We didn't teach it how to do it. There is not much of instruction. As you can see, it can pick P wave, S wave, just based on this image and this timestamp that we provided at the beginning, and just 3 time ticks, which is very close. Actually, it's not bad. I would say it's definitely better than theoretical peaks. Based on that, it estimated the S to P time difference. And then it came up with a very good estimate of epicentral distance, 400 kilometers, which is not far away from the ground truth. It didn't get the magnitude and depth right, which is very difficult. That's another example here with the manual, theoretical, and Gemini's peaks. Another example that I have here for you, these are what I showed you was digital seismic data before that. These are not going back more than 50 years from now. Before that, seismologists used to use analog, different type of analog data. This is one example of them, one form of the multi-channel film seismogram or devil recorder. As you can see, these are very difficult to work with because of that overlap of channels and also the fading part as these are generated by moving beams. Reading the time scale shown by this bond is extremely difficult. You have to count them and then count the time, etc. So that's why most of the effort to digitize this type of analog data were not that successful. So we thought that maybe these models can work directly on this data on like image space. That's an example that we provided to Gemini. Put some instruction, a few examples like this one with annotation. And then based on that, it basically finds this earthquake. It measured the duration of the earthquake. And based on that, the relative time from the beginning of the trace, and it actually estimated the magnitude of the earthquake based on a relationship that I provided in the prompt. So these are just a few examples of what these things can do for our scientific problems in seismology. The ground motion prediction part that I showed you have been already published in a paper recently. That work can open like whole new way of like providing rapid and flexible analysis of unstructured data, extracting scientifically valuable information, it can have multiple potential application in rapid responses, situational awareness, etc. So that was just to give you some flavor or example of things that these can do in seismology. And I think it opens a whole new era of AI seismology, which I call it AI seismology 2.0. So welcome to AI seismology 2.0. Thank you, that was all I had. Another part when I was presenting this to someone recently was that now we know that you can do seismology spending time while you are spending time in TikTok. So no big work is required anymore. So, any questions?
So I have a quick question. So I'm just trying to understand what these social media posts, it seems sometimes in the post it would mention this was 70.4. How much of that information in general is available in the prompt? Like how is it using that information to then predict the magnitude?
Yes, it does that. Yeah, for some, because these are not meant to be in real time. It is just the application of this type of mapping or shape maps are like within a few hours, days from the earthquake. So by that time, usually users, they know the earthquake location, even magnitude. And that turns out to be very useful because, as I showed you, the model used this information with that background knowledge of the ground motion prediction equation, and then to basically justify it or validate what it sees from the post content with what the knowledge of like attenuation of the intensity as a function of distance or magnitude, etc. And then you use it. Actually, one potential application, these type of data are being used, especially in Europe, to estimate the intensity. And one potential application, knowing that these models are using, or there is a like ground motion prediction equation embedded into the LLMs, opens this new type of potential to use this model as a basically as a way to distinguish fake from like realistic reports. There are a lot of like exaggeration. Some people just post fake reports about like destruction of the earthquake that can be easily identified based on that knowledge that model has. So that can be like one form of the application.
I have questions. It's very cool. The first one is, so in the end, will Google try to implement such a thing to actually be used in
I doubt that anybody sit there and train a model to do like ground motion prediction. This is something that they probably picked, and I think there are a lot of similar things related to Earth or other type of like scientific field that they built. We know that they mainly use, they acquire this type of knowledge from the texts that are publicly available. So most of the scientific papers even is not used during the training. We know that they cannot learn that much from the equation, relationship, etc. So mainly from the text and like general information.
And so what do you think is going to be, our next 5 to 10 years? Can talk about more as researchers working in this area. Do you think we could actually combine this kind of information with standard information? How do you?
I think one way the whole thing is going is to make this model more and more capable of doing now, I would say like more advanced high-level tasks, like scientific, like understanding. Physical understanding of the world is very beneficial to the big goal of tech companies, that is to go toward like AGI. So that would be beneficial as much as they can embed the physical work into this system. So one thing, immediate thing is that how we can ingest more high level like physical information into this model. Like in that case, that was showing that it does not know the structure of like mantle or core. So how we can ingest that, how we can improve this, that's one application. But I don't think that's gonna be something that like companies go and do it. This is something that we should do in academia. And then the other thing that for me is interesting is just the knowledge probing and to see what else they know. And the next step would be how they learn these things. That I think that would be useful in a case that I think at one point we may benefit from this type of simplified relationship, for instance, in that case, what it is exactly. You can use it, maybe you can use it in our field.
I guess one of the questions I had, because you showed the data early on that you were using like the different events, and I don't remember what all of them were, but it seems like some of them were likely to be events that would be directly covered like within the training, right? Where there'd be a lot of media reports, like the, large earthquake in Japan. There's going to be a lot of media reports, a lot of information about that on the internet that presumably Gemini would know about, versus some of these other cases were newer. And so there probably wasn't information about those yet in there. And so I guess I'm wondering if you can see any indications of like, for those, was it using information like that had learned about that specific event versus the other events where it's using kind of more general knowledge plus the social media posts? Because I imagine the posts about events where it has a lot of data in the training, like maybe it's not really using that much from the social media. It has a lot of prior information. Is that something that you sort of looked at, like that breakdown of like how much it was likely to have kind of prior exposure to that event versus cases where
I think that's one potential place that probably they learn those relationships, maybe from the like public a website like USGS, because they provide a lot of time the data after the earthquake. But several of those examples that I showed you, especially those with more detail that we look at it, the New Jersey earthquake, it was happening after the release of these models. So we know for sure, like Noto, New Jersey, and also Oklahoma earthquake, none of them were included. None of them happened when they were trying Gemini 1.5 that we use. Some older one may be there, but I doubt, like for the case of Tohoku earthquake, which was the strongest earthquake. When I went to find the ground, I had difficult time actually to find the ground truth because there was so little information going back just to 2011. So I doubt that there was something that they used to gain knowledge about a specific event. And the other thing was that the detail, the good thing is like these details about the analysis of evidence and reasoning that they provide was very useful to see that how they drive into that number, which actually absolutely makes sense. Like the Tohoku earthquake that I was showing, the model even came up with the structure of the building, and it says this should be a concrete reinforcement building, only based on the fact that in caption it was mentioning this is an airport. So it said it cannot be masonry building or wood structure. So based on all, because that structure goes into the intensity estimation. So all of them like make sense. It knows very well the definition of the scale and also how to use information to drive.
I have a quick question. So regarding the intensity estimation, my understanding is that so the Gemini knows something about the intensity, but it didn't really know accurately the definition, because, for example, if your video shows some kind of shaking, right? So the intensity should should stay the same regardless of distance to the earthquake. Is that correct? I understand.
No, I think it knows very well the definition. That's what we sure is available publicly on the thing. And for instance, at the first try that I didn't provide anything, a simple a snapshot, and then it drives. It just gave me directly the MMI intensity, so it knows the definition very well and how to define it. The reason that the values changed when we changed that additional information was that apparently it used those known ground motion prediction equation as a constraint to what it sees. So it doesn't believe whatever it is. That was what I said, that it can be used for like fake report identification, because it used that expert level knowledge with what is evidence and observable on the post directly, and then come up with the reasonable value that makes sense for both of these.
I see. So the sort of an experiential empirical relation for distance is additional thing we consider. Oh, okay. Thank you very much.
So, and that was, I think, the coolest like finding of it. Yeah. Like they know that type of thing.
Yeah.
And that's also different. In seismology, the ground motion prediction equation, they usually have different input output. They use VS30, several other things. So that's what we believe. We think that this is something different. This is simpler, but it makes sense. It was like very similar, like decay pattern, and that was interesting.
Yeah, and I was blown away by your showing the chatbot can pick P wave around as well. That's crazy. I'm wondering, maybe it's this question for Rachel. Have you ever tried it? Post a spectrum and ask the chatbot to pick up the stress drop?
No, if it does it as well as it picks P and S waves, I'm not sure how useful it is.
You can try, but very quickly, because the other thing is this is just a matter of like drag and drop, and you can answer.
Yes.
So that's I think the main point, what I call like AI seismology 2.0, that everybody can do with zero coding. So it would be very easy to find it out.
I know who could do it for me.
Any other questions? All right, thank you very much.